Hi everyone, this is Sushanta again, and we will start with looking at the op-amps. This is a little advanced uh, step from our previous lectures where we understood the basics of a MOS and some basic amplifiers. And now this takes the step to the next level where we go into the two-stage op-amps and the design of the CMOS two-stage op-amps, their fundamentals, the design procedure, and a lot of details. Here I will assume that what I talked about previously, either in my lectures, as I mentioned about the basics, the fundamentals, you already have gone through them, so you have at least some understanding of the basics, because I don't want to explain a lot of them here again when I'm trying to talk about the op-amps. Or you have also, if you haven't seen those lectures, but you have at least taken some courses where you have understood about some the basics, the fundamentals of the MOSFET, the very basic differential amplifiers, single stage amplifiers, how do you calculate gain, frequency response, and all that. So as long as you have that knowledge, I think you're fine. You can go ahead with these lectures to see how we design this two-stage type op-amps and all the details related to it. If you, I would also give you a reference of a very good textbook which I used myself when I was doing my PhD. It's written by my professor there. He was my advisor. His name is Philip E. Allen, also sometimes called as Phil Allen. It's a textbook written by Phil Allen and Holberg. Allen and Holberg is the name of the textbook. It's the authors, and the name of the textbook is CMOS Analog Circuit Design. It's by Oxford University Press. So if you get hold of that, that also has a lot of these materials that I will talk about, will also guide you in much more detail of all these design procedures and of understanding of the op-amps. I'll try to do my best as I talk through these lectures here, but I would also encourage you to look at that textbook or any other textbook that you have in this area. That would be helpful to you. So op-amps, two-stage op-amps is what I say here, but basically op-amps, initially when they came out, they used to be bipolar. They used to use BJTs, very good op-amps, but here we'll talk about only CMOS op-amps because most of the industry now is CMOS focused. All the circuits are made in CMOS. So how do we build op-amps using NMOS and PMOS transistors only? That's what will be the focus. Before getting into the circuitry, a little brief description of what is an op-amp, how do we use it. You have seen it many times. It's a little triangular block which has got two inputs, a positive input and a negative input. Okay, so it's a differential input and it's a single-ended output. Sometimes it could also be differential outputs, but the simplest one of them is like this, where you have a differential input and a single-ended output. And we have used this op-amps as black boxes in various configurations. We use it all over the place. The first configuration I'm trying to show you is a voltage follower or a buffer. You apply an input and you don't want this input to be loaded. You don't want it to be loaded to draw any current out of it. You just buffer it, and this guy provides all the current to the next stage where V out is same as V in. That is the transfer function for this particular voltage follower. Okay, you might have also seen configurations like this, an inverting amplifier where we apply an input. We have two resistors R1 and R2, and if you work it out, the gain becomes minus R2 by R1. It's a simple inverting amplifier. You could also put a capacitor around it called some C2. Then what happens, it not only remains as an inverting amplifier, it also forms a low pass filter at the output. So this is actually acting as a low pass filtering of input, and this is a very I forgot to draw the ground here, the AC ground or a DC bias voltage that will be here, the common mode voltage. So I missed that part, but this is going to implement a filter. So there are various kinds of configurations these op-amps are used. You might have done it on the PCB boards or breadboards, did some experiments, and these are so popular that they are still used in a variety of places when you're doing actually the IC, when you're making this different products, CMOS ICs, whether it's analog ICs or RF type ICs, they all end up using op-amps. In biasing circuitries, in filters, in all kinds of stuff. That's why this is probably one of the most widely used blocks still today. Whether it's analog design or RF design, it's very important to get the basic fundamentals, to get a good understanding of how you design the op amps, all the details of it, because then it helps you become a very good designer, no matter whether you're an analog designer or an RF designer. So this is one of the most critical building blocks that as you go in your career into the industry and design various kinds of circuits, you will be using it all the time. One of the things that I wanted to specify is op amps are always used in a feedback loop. We rarely use op amps in open loop. We do sometimes as comparators, but we will not talk about it. So one thing you have to remember is whatever we are going to do from now on, we will do open loop, but you have to keep it in the back of your head that that circuitry, that op amp will never be used in an open loop configuration. We will always use it in a closed loop configuration with some feedback around it. Like see, this is a feedback from output to input. This is also feedback. There is always feedback there. Why? Because these op amps, which are mostly what we will talk about, the voltage mode op amps, they have very large voltage gain. These are some of the key properties of these op amps that we want from these guys. They need to have a very large open loop voltage gain. That is, from this input to the output, its gain should be infinity if possible. So as large as possible. They should have large input impedance, because when the input impedance is very large, they do not load the input. So this is a voltage source driving it, so this needs to see a very large input impedance, so all the voltage can fall here without pulling any current. So we want large Rn and we need very small R out. This is an output voltage driving something. Its internal output impedance should be very low, 0 if possible. Okay, so these are some of the characteristics of these kind of op amps, which is also represented in this model, where basically you come in with a very large input impedance, which is desirable, and then whatever is your V in, you have a controlled source called AV times V in, AV being a voltage gain. This is the part that we want to be as large as possible. 1,000, 10,000, whatever you can get, big numbers are good. And this will also have a series output resistance, and we want it to be 0 or as low as possible. That is what we will be, some of the key things. These are not the only things. We haven't talked about the frequency response and all that. We will talk about it, but these are some of the key things to start with. Okay, so let's look at a classical two-stage op amp that you will find in most of the textbooks. It kind of looks like this. I will explain it. And if you have seen my previous lecture, you might have seen the stage already that we talked about. This is a gain stage. Okay, it has a differential amplifier as the inputs with a current source, a tail current source, and it has got a PMOS current mirror load. So from this differential input to this point output, we have the gain, and the gain is pretty high depending on GM times RDS, and we'll go through it again a little bit. So this provides the first gain from input to an intermediate output. This is not the final output of the op amp. Okay, so we have looked at it previously, but this is what the stage is. M1, M2 are the input devices. M3 acts as a bias current, tail current source here, and it is being biased by a simple NMOS current mirror that I'm trying to show here. That you have this bias, I bias generated somewhere in the chip, and it comes to you, you take it, you mirror it, and you create two bias currents. One is this bias current. This acts similar like a current source, which is carrying I bias 1. We will also create another current called I bias 2, which is for the second stage. So it's a cascade of two gain stages. This is the first gain stage, and if you take that output and go through a simple inverting amplifier, this is a PMOS type inverting amplifier, and its load is actually a current source load. So here also we're going to get gain from gate to drain, and we'll see what the gain is and we'll calculate all that out. And these two act as the current sources from this current mirror for these two stages. So you have two cascaded gain stages to provide high gain. As we said, that this is an op amp like this, where the input is here and the output is a single ended output, and we want a huge voltage gain as high as possible here. We want high output impedance, which is since we use MOS, these are high output impedances anyway, but these impedances will go down at extremely high frequencies, because what you see there is capacitances. There is no resistance, but there are capacitances that you see, parasitic cap. But at least, for majority of the operation, we will be able to see a high impedance there. Output impedance, I think we'll talk about it more later on, that how do we do the output impedance and all that. So this is a classical two-stage op-amp that is there, and we'll go into a lot of details. But here is the thing that I want to take some time and caution you and want to get something in your head, which is as we go through all these mathematics in the next 4 or 5 pages, you're going to get lost. You're going to go through it again and again and try to understand it, and you're going to get really good at it. But then for the first time when you go and say, okay, I'm going to design this op-amp in the simulator, let's say you have some sort of a SPICE simulator, you start designing it, you throw in some W over L values and you put it and you say that this thing does not work. You know, I have gone through this process myself. I've seen a lot of my friends in the beginning we face it. So there are two things you have to keep in mind. The first point is, as we always mentioned, never design this op-amp and operate it in open loop like this. Do not put it in the simulator. Okay, it has so much of gain that it will act as a comparator. You will never see a good stable output voltage. The output voltage will always rail either to VDD or ground. So never operate in open loop. Operate it in some sort of a closed loop fashion. You have to set it up in closed loop to actually get this op-amp to work. And the second point I want to say is, which is also the first step to this guy, is biasing. We have to make sure these are all biased properly DC wise. And that is one thing I noticed in the industry is people come in and just simply throw in some values and they think that magically it will start working. Well, no, it doesn't. There are certain simple rules you have to do to make sure that you are keeping every device in saturation. That is the only rule. You have some bias current. When you put this bias current, you have to pick this W over L's in such a way that they have to be in saturation. You have to this guy has to have enough VDS across it so that this remains in saturation. This guy has to have enough VDS across it. This current source has to have enough VDS across it. So you have to bias them first. For particular DC bias currents that you have already chosen, you say, I want to burn so many milliamps here and I want to burn so many milliamps here, milliamps or microamps, whatever you want to burn. I need so much of device sizes. How do you get it? You get it from the simple drain current equation. You find all that, and then you have to make sure that they all have enough VDS drop across them so that every device remains in saturation. If every device remains in saturation, then only the small signal models that we'll talk about are going to be true, and we don't want to lose sight of it. So this is the first key step towards designing, is to make sure that the devices do not accidentally get into active region. They have enough VDS across them, they are in saturation, and check that they are getting the right GM and the RDS values that you would expect. Okay, by check I means you do a hand calculation, you know what should be the GM of this input device roughly. Okay, you would know what would be the GM of, let's say, this device. When you bias them in the simulator, check in the simulator to see, okay, yeah, I'm getting an approximate value which is close to what I calculated by hand. So those hand calculations have to be there. Don't just blindly put it, because then what the simulator will give you something at the output, and if you don't understand it, that's not a good process. Okay, so you have to do some initial calculations yourself and then design this to make sure that everything remains in saturation. If everything is in saturation, then and this op-amp is in closed loop, some sort of a feedback around it, then all this that we're going to talk about will fall in place and it'll make sense for you. So let's see, what do we want to start with first. So first we want to start with the gain. What is this gain, the total gain, the DC gain or low frequency gain? We know there are two cascaded stages. So we can break this first cascade stage as something called AV1 and the second stage is AV2. What is the gain of this first cascaded stage? This is what we looked at previously. It's basically the GM of this device and the total RDS looking here. That is RDS6 in parallel to RDS2. Okay, so here is GM2 and RDS2 and RDS6, which is shown here, and that gives you the gain from this differential input to this output. So differential input to single node output, what is the gain? This is the gain of the first stage. Okay, what is the gain of the second stage? This is again a differential amplifier, not a differential amplifier, it's an inverting amplifier. So the gain here is going to be GM7 times the total resistance that we see here. What all resistance we see? Looking up, we will see RDS7, which is here. Looking down, this is a current source. Its VGS never changes, it's fixed. So all you see here is RDS8. So RDS7 parallel to RDS8 gives you the total resistance Anytime there is a voltage here, this will create a current of GM 7 times that voltage, and that's why the gain comes up to be this. So you can see that these are products of roughly GMRDS, GMRDS, right? Two stages. And if GMRDS was 100 as an example, you use long channel device and somehow you're able to get, this will give you a gain of 50. Why? Because this thing will, if RDS, all the RDSs were same, it would become like, RDS by 2. So this first term, the first gain will be 50, the second term will be 50, so you're going to get a gain of about 2500. Okay, so as you boost the gain in each stage, you're going to get higher and higher gain, which is what we want. We want these guys to have very high gain as possible, DC wise and low frequency wise, which is what we're getting by cascading it, the two stages there. Okay. Next are poles and zeros. Before going to poles and zeros, I just noticed one thing, which is a trick thing that a lot of people will ask you, is in this amplifier, if I look at the inputs, why do I have this input labeled as negative and why do I have this input labeled as positive? Okay, why can't we just say, this one is negative, this is the negative terminal and this is the positive terminal? What you do is you have to pick the right terminals in terms of polarity. So what I mean is, let's say this one was positive. Okay, so if the output has to be positive, then if I trace it back, okay, so from here, if it's positive, this point will be negative because this is an inverting amplifier. There is an inversion. So this point will be negative. If this point is negative, this is again an inverting amplifier. You trace it back, then this point has to be a positive. That's why this is a positive. A positive here makes a negative here. That makes a positive here, so it makes sense. This will be the positive terminal. If you increase this node, the voltage here increased, it will increase V out. Okay, so that is the terminology that you will be asked in many circuits, is check which should be the positive or the negative node. Same way you can trace it back here and do it, which will be basically like, so if it is positive, this is negative. If this is negative, this is positive. If this is positive, and this is an inverting amp, so this becomes negative. So now this becomes the negative terminal, because if you increase this voltage a little bit, this node will actually go down. Okay, so that's the negative inverting. So this is the inverting terminal, this is the non-inverting terminal, and that's how you check for feedbacks in many cases to make sure that it's actually a negative feedback system, that it is not a positive feedback system. Okay, getting back to this thing. So calculating the gain, the DC gain, is very simple and it's pretty straightforward, and hopefully by now you're able to look at the circuits and calculate it. Now comes the poles and zeros. Okay, so let's look through what are the different paths that we'll go through. You can take this thing and you can make a small signal model, and you can and you should do that as a side exercise. You should do the derivations, and finally when you found the complete transfer function of V out to V in here, you would see all the poles and zeros there. What I'm showing you is some of the approximate expressions for these poles and zeros that we are deriving here intuitively without getting into the big derivation part of it, and see that how these things, by as a first cut, as a first order approximation, you find them quickly, and how they match up. They should match up pretty close to what you get from a complete derivation. So what are the poles and zeros here? As we talked about, first we have to see what are the nodes we are going to hop through when we go from input to output. So this is my input, one of the inputs, and this is my output. How do I go from input to output? I hop from here to here. So any node I hop through is going to cause a pole. So from here to here we'll get a pole. So there is going to be a pole here. There are some parasitic caps here which will cause loss in gain over frequency. So we will calculate a pole here. From here to here we'll go to the output. Output itself will also have a pole. Right? So these are the two poles when we start from here. When we go from the other side of the input, this is another point that we hop into. Okay, so this will also create a pole. But for this exercise, I'm just going to neglect it. It does not mean that it's so far away that it will not affect us. In many cases it could affect us, so you have to be careful, you have to keep that in mind, but at least in this exercise we will neglect this pole. Okay, next we'll hop from here to here. We are going to consider that pole, so that's actually the dominant pole, the most important pole that we will get here. And then we have, so this is going to have two poles. So let's just talk about the poles only first. Let's not worry about the zeros. Okay, So we're going to go hop from input to output and all and look at it. Input, we are not considering any pole because we are assuming that this is driven by an ideal voltage source, which has got 0 ohms, series source resistance. So if it drives all these parasitic caps here, they're not going to make any pole because there's no resistance associated with it to make a pole. Okay, so that is the assumption here. So what is the first pole that we'll get here? This one is the dominant pole. You find the total resistance here at this point and the total capacitance. What is the total resistance here? The total resistance here at this point is a parallel combination of RDS2 and RDS6, which is what I've written here. This is the total resistance. What is the total capacitance? You see a lot of capacitances here. The biggest one being the CGS. CGS7 is the biggest capacitor, which is the first one I put, and then you have a lot of these things that you can look into it, the various gate to drain, gate to bulk, and all these capacitors which are there. So this is the total resistance. The total capacitance minus 1 over RC gives you the pole. So this will be one pole here. What will be the pole at the output? The output pole again is going to be, you have the total resistance, which is RDS7 parallel to RDS8. Okay, this is the total resistance here, and the total capacitance, I'm just going to assume that CL, the output load we are going to drive, is actually much bigger than any other capacitance. So I can just approximately just put it as CL only and nothing else. Of course, this will come with a lot of other little gate to drain, gate to bulk and all that, but just to keep it simple, with the assumption that CL is bigger, and most of the time you drive a big load. So CL dominates it. So we're going to get this as the second pole, also called as the output pole. Let us not worry about any zeros for now. Let us just worry about poles only for now. Okay, this will have zeros. We will look into it. But let's see what happens when you have, this has two stages, means it has two poles. So if you have two poles, what kind of problems we might get into. Okay, so here is a plot of the frequency response. Okay. So we are saying that this is the first pole, the dominant pole P1, and this is the second pole, dominant. This is the non-dominant pole, or also the output pole P2. Okay, so we have a plot like this. Now, both those poles could be far away, could be closer, could be anywhere. But what is happening is, if you look at this, the RDS is sort of similar. Okay, so RDS terms are there, so they're kind of similar. So they're not going to be very far away because of the resistance part of it. Capacitance part it might, but we don't know which one is bigger, which one is smaller in this case. So I've just said P1 is smaller than P2, but it could be the other way around. This could be P2 because your CL is much bigger, and this could be P1. Okay, so it all depends on what these capacitance values are. So it's not important which one is bigger, which one is smaller at this point, because I'm trying to get a different point to you, which is it could have an effect in systems like this. Wherever you have two poles, it could actually convert a negative feedback system into positive feedback. That is the biggest concern we have, and that's why we go to something called compensation and why it does that. So let me try to explain what happens when you have two poles. Okay, so let's say we have a negative feedback system, like a simple voltage follower like this, where we are applying the input and this is the inverting terminal, and we'll go this way, which I think I've drawn it here again. Now I'm saying that this op amp, which has got these two poles, P1 and P2, okay, so it starts with a very high gain, then this starts rolling down as 20 dBs per decade, then 40 dB per decade. It will hit more poles and zeros, but let's not even worry about it at this point. Let us say that this point is the 0 dB point, or the gain is 1. Okay, so this is the point line, this is the frequency at which the gain becomes 1. For all the lower frequencies, the gain is actually bigger than 1. So here is an op amp where we have a transfer function like this, some DC gain, then 1 by S plus P1 and 1 by S plus P2, right? So these will be the two poles in the transfer function. The question we need to ask is, anytime there is a pole, what does the pole cause actually? The pole causes two things. First, it's causing the gain to roll off, right? The gain to decrease, but also it's actually adding a phase lag. Here we are only showing the gain. I've been only showing the gain, but remember, Bode plot also has a phase component with it. Okay, so because of each pole, it starts to add negative phase. Okay, so it causes a lag. We call it as a phase lag, or a negative phase gets added. And what it says is, if you have a pole location, say P1, and if you consider frequencies, so at P1, what is the phase lag you're going to get? At P1 pole location itself, it will cause a phase lag of 45 degrees. And if you went 10 times P1, whatever the frequency is, which is 10 times P1, you have a phase lag of almost 90 degrees. Okay. This P2, same thing. At P2 it causes 45 degree phase shift, and 10 times P2 it will be another 90 degrees. So you can see that if P1 and P2 are actually smaller poles, by the time we go to where the gain is 1, even before that, we might have certain frequencies where it has completely caused 90 plus 90, 180 degree phase shift. So we have a transfer function which said that from here to here we should have had, so this is the inverting terminal, right? So from inverting terminal to this, if we didn't have any of these poles, what will be the phase shift? We already have 180 degree phase shift. Assume that this HS was just a flat A, okay, a constant value here, no poles or anything. We didn't have this pole 1 and pole 2. What will be the phase shift from this negative terminal, negative input terminal to the output? Since it's an inverting terminal, we have 180 degree phase shift. That is always there, right? Because it's inverting. On top of that, now what has happened is, as we have got these two poles introduced, each of them adding almost 90 degree phase shift, 180 degree phase shift plus another 180 degree phase shift coming from these two poles, with the assumption that P1 and P2 are low poles, and around this frequency where I have the marker, we have already caused 180 degree phase shift, extra 180 degree phase shift because it's two poles. So 180 degree phase shift because it's an inverting terminal plus another 180 degree lag, total it will become 360 degrees, or which is 0 degrees. So even though this is a negative feedback system, going through this op-amp, you're going to suffer phase shifts, phase lags because of the poles. And if you have two poles and both the poles cause 180 degree phase shift, you have converted this negative feedback system into a positive feedback system. This is not negative feedback anymore. Okay. What I mean by that is, if you have lower frequencies, let's say you applied a low frequency input here which was really low, then of course it's negative feedback, right? For the low frequency signal, it's negative feedback. Why? Because these poles have not been able to provide a 180 degree phase shift for that low frequency. But if we were at a higher frequency, like something like this, which is 10 times P2, okay, and definitely more than 10 times P1, for this particular frequency point, these two poles have added extra another 180 degrees. So for that frequency, this is not a negative feedback loop anymore. It has become positive. So if you took all the frequency components possible, okay, lower frequencies, this negative feedback system is still negative feedback. But for higher frequencies, this is tending to become a positive feedback system. That is not good, because we don't know what frequency will come, what kind of noise might be there. Anytime it turns into a positive feedback system, you have a chance of getting hit by those higher frequencies, and it will actually, what happens in a positive feedback system? So if I had an op-amp like this, if I had this frequency component here, just one single frequency component at the input, it will make it, because of positive feedback, it will start growing bigger and bigger and bigger, and it will start to rail, it will start to saturate. What we call as, it will saturate this guy, or it will also saturate or cause oscillations, large oscillations at the output at that frequency component, or even any other frequency component. So all you need is a trigger, a small trigger of any of this high frequency component, and once that comes, either this guy is going to oscillate at some frequency, some high frequency, or it's going to get, go rail to rail like a square wave. So input might be a small sine wave, and output will become a big square wave which swings between 0 and VDD. Okay, so we don't want that. That is not good. So this is the concept that I wanted to explain, which you might already know, that any time you have two poles, each of them giving you a phase lag, you could easily change a negative feedback system into a positive feedback system. Okay, so hopefully this concept is clear now, because these two poles you become, and that's why designing of this op-amp is of course the first step. Okay, it's a key step. You calculate what kind of bias currents we need, what kind of GMs you need, what kind of sizes you will need, and make sure that everything is in saturation. Okay, when everything is in saturation, you will get the gain you want, huge gain, but that does not mean that this op-amp is going to work, because it's a two-stage op-amp. It has two poles, and those poles could be, could be low enough where they, for certain higher frequency components, could turn this from a negative feedback system to a positive feedback system. So we don't want it. For all this frequency, all this region here, right? We always want to remain as a negative feedback system. We don't ever want to become a positive feedback system. The other point, I think I explained a lot here, but one of the things that I missed is, what is the criteria for a positive feedback system to undergo oscillations? It has got two criteria. One is the phase shift has to be 0 degree or 360 degree, which is what we talked about. We have 180 degree from here anyway, and then we are adding another 180 to make it 360. But that is not the only criteria for oscillation. The other criteria is the gain also has to be more than 1. If you have this phase shift happening, but then you never had the gain, then guess what will happen? Any signal here will see a positive feedback, but then it will not be able to cause any sustained oscillations. It will die out because the gain is less than 1. For oscillations or for the positive feedback, along with the phase shift, it also needs the gain to be greater than 1. That's why I mentioned this point, which is 0 dB. Any of these frequencies where the gain is more than 0 dB, okay, that is the only set of frequencies that is of interest to us, where we don't want the phase to shift by complete 180 degree because it's two poles. If you go higher frequencies, right, where the gain has become less than 1, you don't really care because the phase will shift. As you go to higher frequencies, you will have more poles and zeros and all. They will cause more than 180 degree phase shift. That's fine. For those systems, we are satisfying the criteria, one criteria positive feedback, which is the phase has already shifted 360 degrees. But the gain is less than 1. When the gain is less than 1, it's not going to satisfy that the other important criteria for oscillation, which is that the gain has to be bigger than 1. Okay, so we are okay for those frequencies. But we are not okay for these frequencies where the gain is still bigger than 1 and these two poles somehow cause a 180 degree phase shift. We do not want that. Okay, that is what we call as compensation. We have to do is, how are we going to compensate this op amp, and that part is called compensation. So what we do is, as the first step, this is the same op amp drawn again, and I'm going to put a capacitor here called CC. This is called the compensation capacitor. Adding of this capacitor, what does it do? Well, it does a few things. It's going to cause these poles to move. Okay, P1 and P2 will move in such a way that we are going to go to a more stable system where the phase will never shift. Okay, for frequencies where the gain is bigger than 1. So in order to do that, let's first go through some concept here, which is called the Miller effect, and then we'll try to find these poles again. What is the expression for P1 and P2? We'll derive it again. We already did it once here, right? We have these two locations of P1 and P2 without compensation. How will these poles move with compensation? So here, if I just look at this output stage only, and I say, what do we have? We have an inverting amplifier stage. It has some CGS7, some CC here, and we're going to assume the CC is bigger than CGS7. Okay, that's an assumption we're going to make here to simplify things. It has a current source which looks like RDS8. It has the load. So what is the gain of this block here? The DC gain. I should have put an AV to 0 here, but it's actually the DC gain. The DC gain is GM7 times the total effective RDS we see here, which is written here. So this looks more like this. It has an input, it has an output, and it's an inverting amplifier, and across which we have connected a CC. And if you go back and look at what does Miller effect says, there is a theorem by Miller which says that anytime you have an amplifier and you have a capacitor across it, you could break this capacitor as two components, one at the input and one at the output. Okay, and the value at the input will become 1 plus AV times AV2 in this case. So 1 plus AV2 times CC. So it really amplifies. So what the input sees is 1 plus AV times this capacitance value. A huge loading comes to the input. Okay, that is what is seen at the input. Similarly, what is the loading at the output? The output loading is given as roughly AV2 divided by 1 plus AV2 times CC. Okay, if AV2 is very, very large, if this had a large gain, let's say of 100, then it's 100 by 101, which you can just completely ignore and say this is roughly equal to CC. So what this means is, whenever you have a feedback a capacitor across a gain stage where the gain is relatively high, you can break it into two capacitance components. At the input, it gets multiplied by 1 plus the gain of the circuitry. At the output, it's roughly equal to the same value Cc there. Okay, so with this simplification, right, so I'm going to take this Cc and break it down at the input, which becomes 1 plus AV2 times Cc, and then try to calculate the dominant pole. Because remember, this pole was primarily caused by this CGS, right? As we saw in the previous equation, this is the RDS, the parallel combination of RDS 6 and 7, and with all the caps, the dominant one was basically CGS 7, was the dominant cap. Now guess what the dominant cap becomes? The dominant cap now becomes, this is the old values which are already there, which were dominated by CGS 7. Now the dominant one becomes 1 plus AV2 times CC. Okay, so this becomes a huge value, and everything else can be neglected here. So this becomes the cap at the input at this pole where we are causing P1. And so now we can say that the resistance value has not changed because of inserting this single cap. The resistance is still the parallel resistance of 6 and 2, RDS 6 and RDN 2. But the cap has changed significantly, that the pole value has become much smaller. Okay, so what that means is, and I will also show this plot here, let's say this is where, the same Bode plot, this is where our pole was. Okay, this is when we didn't have the CC. Now when we insert the CC, it actually moved it inside by a big time because of the gain of the second stage. By that 1 plus AV2 term, it has moved it significantly inside. So it pulls one pole inside. So the pole that used to be here is now here. Okay, so that is what it has done by inserting this cap to this pole, and it has made it the dominant pole. The dominant pole is also the first pole, or the smallest pole, where the frequency starts to roll off, starts to roll down. Okay, so hopefully it is clear that how we come. So if you did a derivation, you would come to an approximate expression which is like this, but this is a way where intuitively you can find that what is the pole location. Now what has happened to the output pole, the second pole? So this was our output stage, right? What has happened to this output pole? So what has happened to the output pole is, by the time the output pole is caused, since this pole is very low now, let's say if this was say 100 kilohertz, now this is 1 kilohertz, right? So this has moved almost 100 times because the gain, of the second stage that's coming in, and maybe if it's even more lower because CC might be bigger, so it might be even not 1 kilohertz, it could be maybe 100 hertz, who knows? But the bottom line is this pole is so low that after that it starts to go down, right? So what is the definition of a pole? The pole basically says that at this pole frequency, or after the pole frequency, as we go to higher frequencies after the pole frequency, this capacitance starts to get short, right? Its impedance becomes lower and lower. So if we do that assumption that by the time the second pole is going to be caused, the second pole is far away, far out, where this CC, where this was the first pole caused here, the dominant pole, this now starts to act as a short. It starts to act as a smaller and smaller impedance. With that assumption, the CC acts as a short. What will happen if we just put a short across this? What will be the impedance looking here? The impedance looking here, since it is acting as a short, will be roughly 1 over GM7, right? Remember previously, when you didn't have CC, the impedance looking here was RDS7 parallel to RDS8. That was a big value of impedance. Now, since the frequencies are getting higher and this capacitance is acting as a short because we have put in a good enough capacitor, big enough capacitor, the impedance has changed from being an RDS, dependent RDS, to 1 over GM7. So this is what it becomes like. RDS8 is still there, except that now this is not RDS anymore, it has become 1 over GM7. This actually makes a low impedance, and it will push the pole out. The second pole would get pushed out and would have an approximate expression of minus GM7 by CL. Assuming CL is the most dominant capacitor there at the output, this will be this. So what did it do to the P2? So the P2 pole used to be here, which used to depend on RDS and CL. Now it has been pushed out, which now depends on GM times, it depends on the GM rather than the RDS. And GM is a bigger value, means this pole is going to get pushed out, right? So what this compensation has done is, we used to have two poles, P1 and P2, and just by inserting a single capacitor, it has pushed one pole inside, way inside, and it has pushed the other pole way outside. What that has done, so let's say if this was our 0 dB gain point and we were worried about all the frequencies in this range till the gain becomes 1, because whenever the gain is more than 1, we don't want to see a 360-degree phase shift. If that happens, boom, you have a positive feedback system. Since this pole has moved in, it goes in, it starts rolling down, rolling down, rolling down, and till this point we have primarily the effect from a single pole, right? The single pole will cause a 90-degree phase shift here. But now we don't have the second pole, because the second pole has been hopefully pushed far out, where we don't have to worry about the phase lag caused by the second pole. So this has become more like a single pole system. So what happens if we become a single pole system? Where was my picture here? So for the frequencies of interest where the gain is more than 1, this term does not really cause any phase lag anymore, not so much. It will still cause a little bit, but still not a whole lot. This will cause 90-degree phase lag. So from here to here, from inverting terminal to we anyway have 180-degree phase lag. Now we added another 90, so it's 270 degrees, maybe a little more from here or there, 280, 290, whatever. So now we are never going to go to 360 degree. So we are never going to have a positive feedback system for all these frequencies, from DC and low frequencies all the way till this point, okay, where the gain is more than 1. So we will never satisfy the criteria for positive feedback for oscillations, because for all this where the gain is more than 1, the phase never reaches 360 degrees or 0 degrees, so it will be fine. So this is how we compensate an op-amp, by splitting the poles. That is what CC has done. CC has actually split the poles. It has pushed one pole inside and one pole outside, and that is and this frequency point where the gain becomes equal to 1 is called UGBW, unity gain bandwidth frequency. Okay, and there is a way you can represent it in a very simplistic way. Since you have both the poles, right? I forgot to write it in this thing, but this unity gain bandwidth also has a very simple expression, which is GM of this device. Let's say this device is same as this device, right? You can pick any one. So this GM divided by CC is going to become the unity gain bandwidth. How do you get it? You can get it by saying, okay, this is my pole, right? And you have the pole equation here. This is the pole, and if you multiply the pole with the DC gain that we have, that will give you the DC gain of the whole system, or both the stages. You will end up with a value of this as roughly GM1 divided by CC. That is a very simple formula, and that is what you start with by saying that, okay, I want the unity gain bandwidth of this op-amp to be, say, 100 megahertz. I know my input GM is whatever, say 1 millisiemens. Okay, what should be my CC? What is the CC value that I need to start with? Well, GM over CC becomes equal to 2 pi times 100 megahertz. Remember that GM over CC is not hertz, it's in radians. Okay, so you always should not forget that 2 pi formula that comes. So what I mean is, and this is another thing where a lot of people do mistakes, is this does not give you a value in hertz, this gives you a value in radians. Okay, so you have to convert it to the hertz values. Okay, so radians per second rather than being in hertz, so you have to have a 2 pi. So hopefully now it's clear that how the CC is doing a pole splitting, of moving the two poles, how it's making the system more stable, how it's going from a two-pole system and making it effectively more like a one-pole system. So we never have to worry about, till the gain is 1, we are going to lose 180 degree extra phase lag from these poles. No, we'll only lose up to 90 degree and maybe a little more than that. So this allows stability of the system. Otherwise the system could easily go unstable. So any system, not just op-amps, if you're designing any system where you have 2 or more poles, the stability, the compensation becomes a challenge, and that's where you're going to spend a lot of time making sure that you satisfy this. Okay, and there is another term which again I forgot to note here, is called phase margin. Okay, so we have got the term here which is called unity gain bandwidth. But at that point, what is the phase margin? Phase margin is a measure of what is the phase that you still have before you go completely 360-degree phase shift. Okay, so ideally, if it was a one-pole system, you would still have 90-degree phase left to turn from negative to positive feedback. If you have 90-degree phase left, then the phase margin will be 90 degrees. If you have a 60-degree left, it will be 60 degrees. Typically, for all these op amps, we try to design where if you know what your unity gain bandwidth needs to be, let's say it's 100 megahertz, we'll try to make sure that the phase margin is roughly 60 degrees or better to make sure that it is stable and over temperature, over different process corners and all, we are not going to lose that 60-degree number too much. Maybe that'll go to 50 degrees or 40 degrees, but not too much. Okay, because lower the phase margin, the closer it's getting to being oscillatory, and it will have in time domain. So this is all in frequency domain. In time domain, you will have transient response where you might have more and more oscillations that could come up. And I'm going to take a note here. I don't have it here to explain that that how the time domain and frequency domain kind of correlate, in terms of oscillations and how it is correlated to phase margin. So I'll try to do that in another set of slides as we talk about. But for now, so we have taken care of the poles and we have stabilized the system. But we haven't looked into zeros. Zeros are also going to be there, right? And zeros could help or hurt based on whether they are a right half plane zero or left half plane. So let's look at this op amp here. Okay, we go back here and we say, okay, we introduce this, and straight away we can see that there are two paths you can go. You can go through this M7 and come to this output. You can go through the CC and come to this output. Anytime you have two paths combining, that gives rise to a zero, because those two paths could satisfy each other such that nothing goes out to the output. And if zero goes out to the output, what is that frequency? That is a zero. That's why it's the name zero, right? So let's see how we can cause a zero here, right? So this is similar to what we have done previously. We have a path I2 which goes through CC. We have a path. If you have some V here, you will have GM times V here, which creates the current I1. So I1 and I2 could just satisfy each other such that nothing goes out to output. At that frequency, you will have a zero. And unfortunately, in this case, it forms as a right half plane zero, whose value is GM7 by CC. Why is the right half plane zero bad? We'll just look at it in just a minute. But what does the effect on a zero has? The zero actually boosts up the magnitude. What it means is, see, a pole is actually causing a roll off. A zero will actually cause the boosting of it. Okay, so poles cause a negative slope, zeros will cause a positive slope in this Bode plots. Zeros will also give you normally phase lead if it was a left half plane zero. But since this is a right half plane zero, this actually will give you a phase lag, which is bad. And why is it bad? Let's just write it this way. Let's say we have this transfer function from the op amp which has these two poles. But now we have a zero which is 1 minus S by Z. Okay, because it's a right half plane zero. If it was in the left half plane, it will be plus. Because remember, this pole is left half. So I've tried to draw it here, which shows the real axis, sigma, and j omega. Right, this is what we use sometimes to see how the poles and zeros are moving with change in the certain parameters of the circuitry. So here are the two poles which are on the left half of S plane. So this is the zero here. This point is zero. So these are on the left half of S plane. But if you look at this zero, by this expression, that is what, if you solve all the circuitry, will come out as, you will actually have an expression like that. So what happens to the phase? If you take S, so right half plane zero is here. Okay, so if you take S and you present as j omega to see how the magnitude is changing with omega and how is the phase changing with omega, a minus S here is almost similar to saying I have another term here of 1 plus S by something. Okay, in terms of the phase. Okay, that is only true in terms of the phase there. I'm not talking in terms of magnitude. So this actually causes this does not normally add phase. It doesn't do phase leading. It actually causes a negative phase here. Since it's minus j omega, this actually causes a negative phase, just like this guy will cause a negative phase. This pole is adding negative phase. This pole is adding negative phase. This zero, the right half plane zero, will also add negative phase. So if you're adding more and more negative phase, what does it mean? One, 2, and a 3 of them. That actually gets this situation even worse, because remember, as we said, we are going through this. 2 guys were causing negative phase. Now there is a third guy. There is a 0, but it's also causing. It's similar to causing a phase lag, which is also causing negative phase. 3 guys causing negative phase will change this from a negative feedback to a positive feedback even faster. So that's why a right half plane 0 is even worse, because it in terms of phase, it actually acts like a pole where it causes a phase lag or a negative phase. Okay, so this is not good, right half plane. So what do we want to do? We have a right half plane 0 here. Our goal would be that we would try to move this from the right half plane. Okay, so we want to move it away from here somehow into the left half plane. And not only that, you might even say, let's take this 0 and move it right on top of this pole if possible. So how do this move? Even though I've shown an arrow here, normally in this plots they don't move like this. This 0 has to be pushed out to infinity. Okay, so it will only move in the right side direction, and we'll show you how we will move this 0. So we'll move it out to infinity, then from infinity it comes to minus infinity, and then you move it in. Okay, so that is the way it comes in. It cannot just go left side like this, just boom, from 0 it goes left and goes to P2 or wherever it wants to go. No, they always go on the right side, goes to infinity, turns around, and then comes back that way. That is the movement that happens. And I forgot the name of those charts. I know I've done this. This is a part of the control theory classes we used to have where we studied all this, but now I just forgotten the name. It's not coming to my head now. Okay, so let's see how we're going to move this 0 from right half to left half plane. What we do is we used to have this capacitor. Now we're just going to put a series resistor with it, and that series resistor RZ is called the Nulling resistor. So by putting a series resistor, what does it do? Okay, we still have the 0. We have two current components, I1, which is GM times this V here. Now if this is V and this is V out, this is also going to create a current, and then if you solve the two currents and come to the expression for the 0, you will get an expression like this. The 0 will be minus 1 over some R times CC. And what is this? This R has become right now is RZ minus 1 over GM7. This is what you will find out. Okay, so now let's look at it. What happens? Let's say if RZ was shorted, which will be same as before. What does the right half plane 0 becomes? It will become GM7 by CC. This negative sign and negative sign will cancel. GM7 will go up. So it's same as before. So if you didn't have any resistance, you have caused this thing to become actually same as before, right half plane. We don't want it. What will happen if you make RZ equal to 1 over GM? So if this RZ was same as 1 over GM, this thing will become 0, means this will be infinity. It will be minus infinity or plus infinity. When it goes to infinity, you can't really tell, whether it's minus or plus. They are both the same. So, so by increasing this RZ, so this is the point where RZ is 0. As we increase RZ, we are pushing it to infinity here. So when RZ is equal to 1 over GM7, it's at infinity, which is same as this. Then as we are increasing RZ more, it's coming here and it's pushing the pole in, and you could also pick a value of RZ such that, the P2, we have the expression for P2 or wherever the P2 is, that becomes equal to the 0 here. So this is what has happened. This starting point is RZ as 0. We increased RZ, it pushed it to infinity. It came back here, and then we further increased it, and we brought it almost close to the pole, and we can actually place it on top of the pole. What is good if you have a pole and 0? It will actually help with the frequency response, which I will show you in just a minute. Okay, so just wait for that, and we'll go there when we look at this plot here. But before that, I just want to say another extra thing is, we added this RZ, it created a pole, it helped move the pole from right half of S-plane to left half of S-plane and so on. But this also actually, if you derive it, when you do the complete derivation, that's where it will become more evident. It's not very evident here, that this also creates another extra pole. So addition of this RZ has actually created an extra pole, which we will call as P3. So that pole location is approximately given as minus 1 over RZ times C. What is the C? C here in this case will be all the parasitic caps that you have here. Okay, the CC is shorted by then. You have CGS as the main parasitic cap plus all this gate to drain, drain to bulk, and all this capacitance that you have. If you club them all together and multiply by RZ, that would become your extra parasitic pool that you have created. Okay, so always remember, adding something does not come for free. It will always cost something else, which is bad, and the bad thing here is it creates another pole. But hopefully the parasitic caps and this RZ value is small enough where this pole is further out. It doesn't cause us problems. Okay, so RZ you can't make it too big because then it's a problem. This pole will move in and start degrading your phase margin, start causing more and more phase lag. So we looked at the dominant pole here, we looked at the output pole, we looked at how the zero is moving, we also looked at the parasitic, the third pole that came because of RZ. What I have neglected here is I have not talked about this pole, but this is also another pole that will come. Remember, the input from here also goes this way, right? But since it's a low impedance node, you take GM5 divided by all the parasitic cap here, and hopefully that is further out of our interest. But if you're designing a high frequency op-amp, even that pole will also come into the picture. Okay, so you have to keep that in mind. But in this analysis, I have not included that. So finally, by putting all this together, what is the plot we will get? So this is the Bode plot for magnitude. The low frequency gain being, AV1 DC gain and AV2. So that's where the gain we get. We get the first pole as the dominant pole P1, where the gain starts to roll off as 20 dBs per decade. And hopefully, this CC has split the output pole far enough where this is the output pole. And we have also put an RZ in such a case that we have actually brought it from left half of S plane. No, sorry. We have brought it from right half of S plane to left half of S plane and put it right on top of the pole here. So this forms a pole zero pair, and wherever you have a pole and a zero, the slope does not change. They cancel each other and the line will keep going down as 20 dBs per decade. So this whole slope is straight going down. And in design, if you can do that, that is excellent. It's not so easy to do it in a design because of various other factors that come in, but if you do it, this is a very good design. Okay, and P3 hopefully is far enough where it will go and finally the slope will change from 20 dBs per decade to 40 dBs per decade. But that is so further out that we don't care because this is the unity gain bandwidth frequency, which is roughly equal to GM1 over CC. And till that point, it has been a single pole roll off. These things have been far away, and hopefully we have a lot of phase margin, 90 degree or maybe 80 degree, 70 degree phase margin here till this point, which is the unity gain bandwidth where the gain becomes equal to 0 dB or the gain becomes equal to 1. So for all these frequencies where it matters that it could actually start oscillating or could go unstable, we are ensuring that the phase never actually crosses 360 degrees. Our phase margin is at least 70 degree, 60 degree, or even up to 90 degree. That's great to have those numbers, and that is how now we have gone through this whole exercise of designing it. So first step again is biasing it. You have to choose your bias currents. You have to calculate what kind of the W over L you should start with. So you have typically you would like to keep V on numbers to be 200 millivolts. You would like to make sure that VDS is more than 200 millivolts so that the devices remain in saturation, and that all the GMRDS, because anytime a device goes into active, you will lose GM and you will have very pathetic RDS, as we have seen previously in the devices operating in the linear region. So we don't want anything to operate in linear region. We want them to be biased in saturation all the way. And then once you have done it, you compensate it. A simple compensation scheme here. And that kind of hopefully gives you an idea. Before concluding this lecture, one of the things I wanted to just point out is you can see that here I put the resistor as a resistor with a cap here, right? So first is a resistor and there is a cap. Here I'm trying to show as a cap and a resistor. Sometimes these caps are made as out of MOS devices itself, like a varactor or something that we kind of talked about previously. If that is the case, then it is not good to put this cap at this output, because when the signal swings here, this could have a large swing. You don't want a large swing to be seen by a capacitor, because then it will make the capacitor nonlinear. Its value will change. So when you're putting a CC, you want the CC to be constant, and you want the voltage swing across it to be as low as possible. That's why you try to put it not at a node where the voltage swing would be large, rather you put it at the node where the voltage swing will be smaller. Remember, there's a gain here, right? Going from this point to this point, there is huge gain. So for example, if this was swinging 100 millivolts and this GMRDS value was say 100 as an example. Okay, then 100 millivolt swing will cause a 1 millivolt swing here. So this is a very quiet node, it doesn't even move much. So you would like that non-linear capacitor, like a MOS type capacitor, to be attached here. Resistance value normally does not change. Most of these resistors are poly resistors, and even if the swing changes across it doesn't really change their resistance. It's just a piece of poly whose resistance is just always the same. It doesn't change with the voltage swing. So that's what one thing I wanted to point out here is sometimes we do a mistake of putting a capacitor here, which is large swing, and then if the capacitance value changes, then what it is meaning is this P2 pole, which is caused by this P1 pole, which is caused by that, and P2 pole is also dependent on that. These are moving over voltage swing, and you could actually see instability issues. You could see more oscillations, and all the stuff could come up, even though you said, oh, my CC value is supposed to be this, but then the CC value changes with voltage swing. Okay, so you don't want that. So that's another point I wanted to make. And so let's wrap up this lecture here, and we'll continue on with more details of the same topology. And I will also add more details, as I mentioned, to some of the things that I could think of while I was talking to you. Let's look at the stability and the phase margin aspect that we talked about into a little more detail. That how this is, what kind of problems does it cause? We already explained about it. A negative feedback system turning into a positive feedback system for some higher frequency values, where the gain might be bigger than 1 and the phase has undergone a 180-degree phase shift. So let's revisit that again and I'll try to give you a little more information on what that really causes. So let's start with this plot, which we have seen. This is the transfer function, the magnitude plot. Till now I've been only drawing the magnitude plot, but along with that I've also added the phase plot here, which I realized it's also important to understand that how the phase is changing and look at it and then define what the phase margin is. So let's say if we have a two-pole system such that the second pole is actually caused beyond this line. This is a 0 dB point. Okay, so we call this point as the unity gain bandwidth frequency, where the gain has become 1 or 0 dB. Then what will happen is at lower frequencies, the phase in the beginning, the phase will start from 0 degrees. Okay, there is no phase shift at all. But by the time we come to this pole location P1, the dominant pole, okay, at the pole location, as you all might know, that it goes through a 45-degree phase shift. Okay, so 10 times lower frequencies, almost no phase shift, then the phase shift starts happening. At the pole location, you see 45-degree phase shift, and then at 10 times the P1 frequency. So let's say if this frequency was 10 times P1, it would go to 90-degree phase shift. Okay, so the P1 has caused 0 to 90-degree phase shift, and it will remain this way. And then what will happen is it will remain 90-degree phase shift because P2 is further out as per this diagram, and that's what the op-amp compensation tries to do, is push the P2 out, push P1 inside. Okay, so the phase will remain at 90 degree, minus 90 degree, because this is a phase lag, or it's adding negative phase. And then at the unity gain frequency, hopefully this P2 is far enough where it does not cause so much of phase here. The phase will start to move again. At P2, at this point it will be 135 degrees. Okay, so we're minus 135 degrees, and at 10 times P2, this phase will go away to minus 180 degrees. Okay, so since we have only two poles in this particular example, in this picture, okay, I did not add any zeros, or I did not add any further parasitic poles to make this look more complicated, but just wanted to show you, because of two poles, how the phase changes. And at this frequency, which is where our unity gain bandwidth frequency is, we come and look at the phase, that how much phase is there till 180 degrees. How much more phase shift could happen till 180 degrees, and that margin is called phase margin, which is sometimes we call it as PM, means phase margin. That is the amount of the phase. Typically we try to design it to have 60-degree phase margin, because over this point, if you simulated your circuit and you said this is the point, this is my unity gain bandwidth, that point will never remain fixed. Over temperature variations, over process variations, this will shift. So as this point shifts, your phase margin will also change based on, because these poles will shift a little bit, this frequency will shift a little bit. So that's why we start with a 60-degree phase margin typically, which might degrade to say up to 50-degree, which is acceptable, or could become 70-degree, which is even better. So that's why we try to always target a phase margin of 60 degrees for this kind of the systems when we are doing compensation. So hopefully now it's more clear that with this Bode plots where we have both the magnitude plot and the phase plot, and how we determine the phase margin. And when you actually do simulations and you do simulator, you will determine this margin, that how much extra phase can I go more before I hit 180 degrees. That is the phase margin. Okay. Let's also look at what does this phase margin does, and this is I'm going to explain this with respect to this configuration here, where the op-amp is connected as a unity gain buffer configuration. Okay, this is the input, this is the output. Now what could come at the input is, the input does not necessarily just need to be a single frequency sine wave. It could be, but in many applications we also use square waves. Okay, so in many kind of applications it could be square waves or it could be triangular waves. What it means is, if you take the square wave case, square wave is the worst, because anytime you have a square wave where I'm only showing like a rising edge of it only, like a clock, I'm not showing the falling and rising on, but let's just refer to one particular edge only. Anytime you have a fast rising edge, right, that corresponds to high frequencies. Then all the harmonics, so for example, if it was a clock of some frequency f, okay, you're going to have the frequency. If you do a Fourier analysis and you expand it in frequency domain, it will have frequency components of f, it will have 2f, it will have 3f, 4f, 5f, and goes on. It'll have it till infinity. So a transient waveform is really a good example if you wanted to excite this with all the frequencies. You can see that when it goes high or low, it is fixed, means it's more like DC. So it has all the low frequencies, and the sharp transition means it has high frequencies. And also, from if you do the Fourier analysis, you will see the same intuitive thing that we just talked about. It excites the circuit with all kinds of frequencies, low frequencies as well as high frequencies. So now if we go back here in this plot, you have low frequency components as well as you have these frequency components, you have high frequency, all these components are there. So we're exercising all these frequencies, right? And that is a good way to test the stability of the circuit, because as I said, when you have low frequency components, you know, these poles don't cause enough phase shift, so you don't have to worry about that whole problem of negative feedback becoming a positive feedback. Okay, that does not really happen for low frequencies because the phase shift is not happening here. But at higher frequencies, when the phase shift is happening more and your gain is still more than 1, you have a problem. You could have a problem there, because those high frequency components could start oscillating, could change the system to a positive feedback, and could start really causing, you know, oscillations there. That is what we are trying to see. So to excite it with both low frequencies as well as high frequencies, all the frequencies, we put in a step kind of a wave, and we look at a transient, and from the transient we can determine how good is the phase margin. So how do we correlate it? How do we correlate this frequency domain information to the time domain response? How do we correlate it? That's what I'm trying to kind of show here. So this is your time, and this pulse is what I put in, called V in. Okay, it's a pulse, it's a fast rising pulse. Corresponding to that, the circuitry will react, and it will, let's say the output was here, it cannot go so fast. You know, it has some limitations. It has to go through some slewing. Its output response is limited by the slew rate of this op-amp, which we'll look into more later on. But first it will start going this way, and then it could have two kinds of settling, which is not two, many kinds of settling, but I'm just showing two of them here. If you perfectly have a 60-degree phase margin, okay, that would correspond to this green settling, which is what we call critically damped systems. If you, which you must have learned in the control theory, is you have different kinds of systems, closed loop feedback systems, critically damped systems, over damped systems, and under damped systems. This green plot for 60-degree phase margin is a critically damped system. It goes and it just settles to it quickly without any oscillations. If the phase margin is less than 60 degrees, which is what we call as underdamped systems, okay, which are tending to be more unstable, then you would actually go up and you will oscillate a few times and then settle down. You will still settle down, but you would tend to oscillate a few times and settle down. These number of ringings is proportional to the phase margin. So if the phase margin, there is an analytical expression somewhere where you can look at the number of ringings. If the number of ringings were 2, that means a phase margin of about what, 50 degrees or something like that. So as the phase margin reduces, as the phase margin becomes worse and worse, you will see more and more ringings. As the phase margin tends to go to almost 60 degrees, you get an almost very good settling without all this. Okay, now if the phase margin was more than 60 degrees, which is what we call as over-damped systems, you will have the same kind of response, but it will be more sluggish. It would go out more sluggishly, slowly, and then settle down without any of these ringings. Okay, so that's how phase margin, in a way, looking at the thing, you can predict that what the phase margin is, or if you have designed it for a particular phase margin, you know what to expect when you put it in a closed loop feedback like this, that what the response should look like. Okay, so as the phase margin goes down, goes bad, you will see more and more ringings in this settling. And why is this bad? Because this guy, there is a thing called settling time. You will see that when you apply an input, this is a buffer. When you apply an input as a square wave, you want the output to be square wave, and you want the output to settle quickly. The more it rings like this, the more time it will take to settle down, and it will increase something called settling time. We don't want it. Okay, then it's not a good op-amp. You want this buffer to be a good buffer where the settling time from input to output is as small as possible. Okay, so it causes these settling problems which you don't want. So hopefully now you understand the correlation between the frequency domain information and the time domain information and how these could have an effect. So let's say if you were designing an op-amp, okay, and we will actually next we'll go through an example of designing an op-amp, but what I was trying to say is if you design an op-amp and you wanted to really see how stable it is, you would of course design it and find similar and get the phase margin, but do not treat this as the ultimate golden standard for stability. If you want to know how stable your op-amp is, this is only giving you partial information. What you should really do is put it like this, or in the configuration that you're using. You will always use an op-amp in some feedback configuration, inverting amplifier, low pass filter, or whatever it is, switch capacitor circuit, anything. In that configuration, hit it with a square wave. Hit it with a square wave clock and see how the output looks. That is an ultimate test for your stability. So always do that. Never just rely on this information only. Always do a transient stability check to make sure it is stable. Okay, so we have gone through this op-amp. Now we'll try to go through a design example, and I will walk you through some of the steps which you can use to design this op-amp. You might have your own ways also of doing it, which is fine because everybody has their own way of doing it. There is no one unique way to come to the design of this op-amp. You could do it in many different ways. This is one of the ways which I just thought of sharing with you. And the other thing is, this is also going to be iterative. You're going to find various things in this process, one step after another, and many of the steps will be iterative, which is not shown here, but you will need to do it. But this would give you an initial idea of how you can approach it, and then as you understand it better, you will get good at it. You can do more iterations and fine-tune your design. The purpose of this test is to actually come up with a first cut hand design. Okay, something that you calculate paper on a paper, with pencil and paper, and you draw the circuitry, you come up with W over L values, you come up with things before you go to the simulator. Okay, do not go to the simulator quickly. That's a lot of the folks I've seen do that. Do not do that. Try to at least come up with a first cut design like this on paper, which is what this is, and then go to the simulator for fine-tuning it. So we're going to design this op-amp, the two-stage op-amp that we looked at. We are going to assume a few things. Let's assume that the VT, whether it's for NMOS or PMOS, is 500 millivolts, okay, for both of them. And we will try to design all these devices with a V on. V on is VGS minus VT, or also called VDS sat sometimes, the saturation value of VDS. That is a 200 millivolts, means you need to keep VDS at least 200 millivolts to keep these devices in saturation, and we want to make sure every of these devices are in saturation. Okay, so we will use V on of 200 millivolts. We will also use K prime. K prime is an element that is a parameter that you need in the drain current equation. If you are trying to find the large signal drain current equation, you have the parameter there called K prime. So K prime for N, for the NMOS, let's assume it to be 200 microampere per volt square. For PMOS, let's just assume it to be 100. These are not tied to any technology or process. These are simple values that I'm just using right now to go through this exercise. Okay. We will also assume that let's try to drive a 5 picofarad load. The load that we are driving may be up to 5 picofarad, and we'll try to use it as a buffer as shown here, where this output terminal would actually come and be connected to this input here, the negative input. Okay, so V in we will apply here, the positive terminal, and whatever we apply here, it should show up here. Okay, it acts as a buffer. But how much load is it going to drive? Let's say it's up say 5 picofarad load. How fast do we want it? Maybe we want this op-amp to be, say, 10 megahertz, 100 megahertz speed. Okay, so let's put the unity gain bandwidth of this op-amp to be 100 megahertz, and we want a phase margin of 60 degrees or better. Okay, so let's start with some of the formulas that we already know. We know the unity gain bandwidth is roughly GM1 over CC. Right, we looked at it previously, and that is equal to GM1 over CC is the unity gain bandwidth. GM1 is this one, CC is this compensation capacitor. We want that to be 100 megahertz. Now remember, this is in megahertz, so it is not just GM1 over CC, it's GM1 divided by 2 pi CC. Okay, otherwise this is not going to be in hertz. This term itself is going to be in radians per second. So we don't know GM1, we don't know CC. We can assume we can go through it, but that's what we're going to do. So let's just wait a minute, but we'll be there. But first, let's try to do this. Let's try to draw the Bode plot and see what are the things we know in this. We know that the unity gain bandwidth is 100 megahertz. We have not been given what is the AV0 gain, and we don't need to be, because see, the goal of an op-amp is you want to have as much high gain as possible. This depends on GM and RDS. Okay. We are not worrying about what the RDSs are. What we are going to do is we are going to keep them in saturation, and whatever the technology provides, the best RDS, we will just make sure that we can get the best gain possible. Okay, so this is not a parameter that we will be designing to here. We just want to get the best we can, and hopefully, the RDSs are large enough, which is dependent on technology, dependent on lambda. Our goal is to make sure we keep them in saturation. Okay, so we'll do that exercise. So I'm not really going to derive this or that what the gain is. We'll just live with whatever value we get. The first dominant pole. The first dominant pole is again a function of this gain of the second stage, right? So we will not derive it. It doesn't matter what the dominant pole is. What matters is the unity gain bandwidth, and we should be stable here. So that is what we will look at. And also, for us to be stable, we don't need to worry about this dominant pole P1. We really need to worry about where is P2, where is the 0, and also other parasitic pole like P3 that's caused by adding this Nulling resistor. Okay, so we need to be worried about those things. So we assume here that, okay, if my unity gain bandwidth is 100 megahertz, let me assume we do want to keep it out of this point, because the more further we keep it out, the better it is. We will get better phase margin. We will have less phase effects from this guy, so which is good. So let's say we keep it at 200 megahertz, just as an example. Remember, this is going to be an iterative process. You start with some assumptions, some initial values, and this is one of the initial values. Okay, so P2 is 200 megahertz, and we say the 0, this Nulling resistor is going to give us a 0, and we'll try to put the 0 right on top of this pole, which also is a 200 megahertz. Okay, so here is the expression, approximate expression for P2. Here is the 0. We'll look at all this again. So we are going to keep both of them at around 200 megahertz. So what is P2? P2 is minus GM7 by 2 pi CL. Right, that is the expression of approximate expression of P2 here. GM7 is here, CL. CL we know. So we can derive GM7 from here as 2 pi CL, which is 5 picofarads, and the P2 location we are looking for is 200 megahertz. All this will give you a GM7 of 6.28 millisiemens. Okay, so that's how we find the value that, okay, in order to keep a pole here at 200 megahertz, and in order to be able to drive 5 picofarad, this GM should be 6.28 millisiemens. Okay. So that is 1 GM we have found. Next, what we will do is the input part, we will just make another assumption that GM1 is 1 millisiemens. We'll assume that the GM of this guys is, let's say, 1 millisiemens. Okay, this is again another assumption. You can assume it to be more or less or whatever. It's all fine. It's an iterative process because at the end you have to satisfy all the criteria. Here I will just assume this is 1 millisiemens. If I assume it 1 millisiemens, unity gain bandwidth is roughly minus GM1 by CC by 2 pi. From here, you will get that if GM1 assumption as I made is 1 millisiemens, it will give me a CC, a compensation capacitor of 1.6 picofarad. Okay, so we have found what should be the value of the compensation capacitor, and that is from the 100 megahertz unity gain bandwidth. Next, what we will do is we also said that P2, the output pole, and the 0, the nulling resistor 0, we want them to be equal to get better phase margin. Once we do that and we put the equation for, this is the equation for the 0, this is the pole, we cancel all this, we'll get 0 as 1 plus CL over CC times 1 over GM7. We know GM7, we found it as 6.28 millisiemens. We know CL, which is 5 picofarad, CC is 1.6. If you put all these values, it will come to about 657 ohms. So what it's telling is that is the value of the RZ. Okay, so this is the scenario we wanted to have. We wanted to have a unity gain bandwidth. We wanted to have the pole and 0 here, and based on this, we have found some values. We have found that GM1, GM2 should be 1 millisiemens, GM7 should be 6.8 millisiemens, CC is 1.6 picofarad, RZ is 657 milliohms, 657 ohms, and this will give us roughly a unity gain bandwidth of 100 megahertz, and the second pole and the 0 will be roughly around 200 megahertz. We don't really care about P1, the dominant pole, because that is so low, it doesn't really affect us. We only worry about frequencies from unity gain bandwidth, and around there, all the parasitic poles and zeros which are degrading our phase margin. That's what we care about. And P3, well, P3 is dependent on a lot of the parasitic capacitance, especially the CGS of this M7. Since I don't have it here, I will not worry about it, and I will make the assumption that, hey, P3 is somewhere far enough so it doesn't affect my phase margin, and I will not calculate P3. I will go ahead and put this design in the simulator, and then I will see whether P3 is too big and is causing me a problem or not. Then I will go on to the fine-tuning mode. So here I'm not calculating P3 because then it will need me to require a lot more process parameters and all that, like COX and all that stuff. So I'm not doing that one here. Okay, so now the question to ask is, this is great, we have got all these values, but then what do I do next? Remember, we said GM1 is 1 millisiemens. How is this guy going to give you 1 millisiemens? Well, it has to carry some bias current, and it has to have some W over L values. We have not calculated any of that. So how do you put it in a simulator, okay, without knowing those two information? And you can't. That is what we have to derive next, is we have to now bias these guys, bias these two legs, bias the output stage, and find all the W over L values. Then only we have finished our approximate design on paper, and then only we can go to the simulator. So how are we going to do this biasing? How are we going to find it? This is what is next. Okay, so we're going to start with we will make another assumption here, which will be, let me assume that the bias current in this M1 and M2 transistor is 100 microampere. Okay, and why is it so? So first of all, let me go back and see. So I made an assumption that these two GMs are 1 millisiemens. Okay, they could be caused by different bias currents. I'm also making an assumption that let's make the bias currents of about 100 microampere. Why? I'll tell you why I made the assumption is, remember, whenever you have a bias current, from there you can calculate the GM, right? So GM is 2 times IDS by V on. So if V on is 200 millivolts, which is what we are trying to design, and I keep the bias current as 100 microampere, if you put these two together, you will see the GM will come as 1 millisiemens. So a bias current of 100 microampere will satisfy a 1 millisiemens GM. So I didn't really need to assume it. I could have just come here and calculated that what is the current I need to get a 1 millisiemens GM from this equation. I could have done that too. Either way, it will give you 100 microampere current. So what it tells us is we need 100 microampere here, 100 microampere here, means this tail current has to be 200 microampere. Okay, roughly, as is the initial starting point. So we have found the current. Now we need to know how big these devices need to be, right? So we still don't know that. So how do we find the devices then? So we have the IDS. Equation is K prime W over 2L V on square, right? V on is 200 millivolt. K prime we know for these NMOS devices is 200 microampere per volt square. So if I put all that in this equation, 2 times IDS by K prime V on square. So IDS is 100 microampere, K prime is 200 microampere per volt square, V on is 200 millivolts, square of that. If I put it all in, it will give me a value of 25. What it means is W over L value for 1 and 2 has to be 25. Okay? So what that means is if I chose L as 1 micron, let's say, then W will be 25 micron. If I chose L as half a micron, W would be 12.5 micron. What I would try to do is use a long channel device, okay, to make sure that all these equations are valid. But I have not told the technology yet, whether it's a 1 micron technology, 20-30-year-old technology, or whether it's the latest technology, which is say 28 nanometer or 14 nanometer, right? So this W over L gives you a relative value. Okay, it does not tell you what the value of the L is. That is a choice. You have to choose it judiciously, that how long the channel length has to be to make sure it's long channel, but it's not too big. You know, you can always come and say, hey, it's a 28 nanometer process, and if I choose, 5 micron length, that's a long channel. Well, of course it is, but then the devices are going to be so huge, the area is going to be huge. So we always try to lower the value of the L, but not lower it too much, where we start getting short channel effects or where the channel lengths are not long enough. Okay, so these values will give you a W over L ratio. You have to choose what is the L that you want. Okay, so that's the point I wanted to make. So we have now, so what we have done is we know what is the bias current here. We know the device size also of M1 and M2. Okay, now let's see what is the other device size I find out next. Next we find out M3. Same way, M3 is the tail current. That is this guy here. Sorry for going back and forth all the time. I didn't have the picture on the same page. This is the tail current here. So this will carry 200 microampere, which means that if you put it in the same formula, you would get a W over L of 50. Or it's twice of the W over L of the M1 transistor, which makes sense because it's carrying twice the current. Next we're going to find M5 and M6. M5 and M6 is actually these two PMOS devices here, right? The diode connected PMOS current source load. It's acting as a load there. So there also we'll do the same thing. We know that they are going to carry 100 microampere current. The only difference is we now need to use the K prime for the PMOS, not the NMOS, and that is 100 microampere per volt square. We still use that. Okay, let's just keep Vn of 200 millivolts for all of them, and when we do all this, it will give us a value of 50. So there the W over L values have to be 50 to 1. Okay. Finally, we find M7. This is the output device, the output PMOS device, the final device here. Okay, how big that has to be? That is, oops, too much. Okay, there what we have to do is we know what the GM has to be. So now you will find out what should be my biasing current. We have not found the biasing current in the final output stage. So we'll use this equation again. GM is 2 times IDS by V on. If V on is 200 millivolts, GM we know, IDS will come to be about 628 microamperes. So the output stage has to be biased around a current of roughly like that, such that the V on is 200 millivolts. Okay. If you know the current now, then you can find W over L from this equation, right? 2 times the current. Current is 628 microamperes. Kp, it's a PMOS transistor. Put it as 100 microampere per volt square. V on square, and it'll give you about 314. So that's a pretty big device at the output because it has to carry bigger current. So as we have done this, now we have come to this point where I think our first cut design, is ready. So let's say we have a 100 microampere bias current. This will be 25 to 1. And I'm just assuming 1 micron channel length. Again, what is the channel length? You have to choose it based on the technology. So this is 25:1, which carries 100 microampere. This is 50:1, we found that, which carries 200 microampere. These two are 25:1, 25/1 for the input devices. They carry 100 and 100. These are 50/1, 50/1. This is the one which carries a huge current of 628 microamperes. 314:1 is the size. And here is the size. We didn't find it, but you can find it the size based on, we know the current. You can easily find based on 200 millivolts V on, you can find this. We also found the RZ value and the CC value. Okay, so that gives us the biasing currents and the W over Ls, and also the DC voltage. The DC voltages are important because remember, we did not check the DC voltages. We have to check the DC voltages here to make sure that all the devices are in good saturation. Otherwise, these assumptions we made will not be valid. So we started with saying that let's say the supply is 2 volt to give us enough supply. Maybe the inputs are at 1 volt, which is half the supply. Okay, so here the voltage will be 700 millivolts here, because that is VT plus V on. VT is 500 millivolts, V on is 200 millivolts, so it's 700 millivolts. Same here. If this is 1 volt, this is roughly 300 millivolts, right? So we have a V on of 200 millivolts, 300 millivolts across this, so it's still in saturation. We would love to have this a little bit more, but we'll live with it for now. So this keeps this current source in saturation. This is 1 volt here, 1 volt here. What are these drain voltages here? So for that we have to come from the top and say if this is VDD, we go down VT plus V on. So this is 1.3 volts. So this is going to be roughly 1.3 volts. This is 300 millivolts, so this device has 1 volt VDS across it. That's great. That's a lot of voltage to keep it in good saturation. So this device is in saturation. This is of course in saturation. This is also in saturation. We are good. How about this side? Well, what is the voltage here? The VGS here is again VT plus V on. So this point is also 1.3 volts. Same as this. So this device also remains in good saturation. All the devices are in good saturation. Okay, this has a VDS of 700 millivolts, great. This has a VDS of 1 volt, that is also great. So they are all in saturation. And of course the output is also in saturation because the output voltage, since we are connecting as a buffer, if the input is 1 volt, the output also becomes 1 volt. So this will be sitting at 1 volt. We have 1 volt VDS for both the PMOS and the NMOS. Okay, so this completes the exercise of designing this op-amp. A simple first cut design. So you will take it, you will put it in your SPICE simulator, and you will start tweaking these things now. Remember, what we have not found out here is, given that I have not used the process technology, what is the COX value, what are the actual W and L values? I'm only making an assumption of 1 micron here, right? You could be using 0.5 micron. Based on those, you're going to have all these parasitic capacitances. Based on those parasitic capacitances, you will find out where is the P3 pole and all the other poles. So in this exercise, it is not possible for me to give you an exact phase margin number. But we kept these things far enough, and also the pole and zero, to make sure the phase margin is better, is at least 60 degrees or better. But how to get an exact phase margin number, how to get an exact unity gain bandwidth number, that is something that you're going to get from the simulator when you put this design. And if you don't see exactly what is happening, the parasitic poles are making an effect, then you have to go back and iterate this design a little more. You have to change some sizes to reduce parasitic capacitances. You have to probably change, say, I can't just live with V on, the same V on for all of them, and things like that. So you will go through an iteration, but this is the starting point. This is a good starting point before going to the simulator. Okay, so we have done that. Now, after we have done this design, let's go through some of the other things which are important for op-amps that we talk about. Some of the other things which are important. One of them is the input common mode range. Okay, so when you look at this op-amp, right, I said the input was biased to say half VDD. VDD was 2 volts, I biased it as 1 volt, but it's not going to remain at 1 volt. This is a signal coming, it could be a clock. It will have a low signal, it will have a high voltage. So what levels of voltages can this guy carry? Okay, and that is what we call input common mode range. Common mode because whenever there is an absolute voltage here, this also tends to be at that voltage level, right? That's what this will do, because you have so much of gain and you put it in feedback, then what it does is the positive terminal and negative terminal are almost at the same voltage. That's what we call as virtual ground, right? These two are at the same point. But the input, this voltage level could be high or low. How high can you take it? How low can you take it? So let's do a simple analysis here for the input common mode range. So here is the input, and of course I'm not showing the output stage and all the other things go with. I'm only focusing on the input part. I want to know how high can I take this before I break the circuitry, and how low can I take this. So first let's go with the max input common mode level. Okay, so this also high and this also high, so that becomes common mode. It's not a differential signal, it's a common mode. By common mode, what you mean is you are taking the differential inputs and you're moving both of them the same way. They both will go up and they both will go down. Okay, so that is what is mean by common mode. So how high can I take this and simultaneously also take this up? So we know this voltage is VDD, so this becomes VDD minus VT minus V on. Okay, and then if this is at some voltage level, say V in max, not just this but both of them, okay, since we are doing a common mode, they both are going up. So if this is the value, what is the value here? It will be V in max minus VT minus V on. Right, so we know the voltage level here, we know the voltage level here. What is the VDS across it? Because remember, we have to make sure we keep this device in saturation. This device is always in saturation, so is this. This device is in saturation when we go, because we are taking it up. When we take it up, this node will also tend to move up. Means you are only increasing VDS here, so this current source is always going to be happy. The only guy who's not going to be happy is this VDS, which is now trying to getting squeezed. Right? So if I write the equation for that VDS, that will be the top voltage, which is here, the drain. The drain voltage is here, and this is the source voltage. So if I subtract the two, I come up with this expression of VDS. You want to make sure that this VDS, you always maintain a V on, okay, to keep this device in saturation. Otherwise, when this device goes to active, it will start losing gain, and the op-amp will not do what we want it to do, is to provide high gain and with all the devices remaining in saturation. That will not be true anymore. So if VDS has to be more than V on, you can take this same expression, say this is the VDS has to be greater than or equal to V on. From here you will get that the V in max, the maximum common mode level I can go up, is actually a V on away from VDD, which is great. So what that tells you is you can take this voltage and take it almost to VDD. Almost. How much away from VDD? By an amount of V on, to ensure that we maintain a V on here. So this op-amp configuration will work great if this input increased almost to VDD levels, okay, till VDD minus V on. So if it went up, if it was a clock, it went up to VDD minus V on, great, it will still work and the output will be that. We will still have large gain and all those good things about op-amps will be true. Okay, so that is the maximum input common mode level. How about the minimum? In minimum, what happens when you lower it? This also goes low. Now you will start to squeeze this current source. You will try to knock it out of saturation into active. We don't want that. Okay, we don't want this current to be reduced. Okay, so we want it in saturation. So what is the minimum? The minimum is actually simpler to find. This will need VT plus V on, and we need another V on here. So the minimum tends to be VT plus 2 V on. Okay. So that becomes the minimum. So, and that gives you the levels that we are looking for. The highest level of this input common mode is roughly VDD minus V on, and the lowest level you can go to before you start squeezing this current source is VT plus 2 V on. Okay, so within this range, if you had a square wave, if you have a square wave input here, right, or a sine wave or whatever wave you have, where this is trying to do a buffering, a good range of levels that this could be swinging at would be this. If you exceed these levels, this op-amp will start having more non-idealities, its gain will go down and the output will not be equal to input, and a lot of things will happen. But as long as you're within this range, you will be alright and the op-amp will do really good for you. Okay, so this is with the input common mode range. Similarly, you can also do output common mode range, but I did not actually put that as a section, but I can talk about it. Okay, I can talk about output common mode range. or the output range. In this case, it's really not a differential output. It is a single-ended output, so there is no differential or common mode type of thing. It's just the output range. So how high can you take this? Well, you can take this high by still keeping this in saturation. So that would be VDD minus V on. So VDD minus V on would be the highest point you can take the output to while keeping this still in saturation. And how low can you take it is another V on from ground. Okay, so the output levels is kind of pretty good, pretty symmetric. Is you can go all the way to VDD, except you have to be a V on away from VDD and a V on away up from ground. So that is the output swing level. But hopefully that is clear. You know, both the input levels that you can have for a signal and the output level for this op amp. And based on this input and output levels, as you see, there are limitations. It's not going to cover the output. The input will not cover 0 to VDD, right? So this one does not. And how can you go 0 to VDD? There are different configurations of op amps where you will use a complementary NMOS input stage and a PMOS input stage and do all kinds of fancy stuff, so they can actually handle a full range of inputs from ground to VDD. Okay, so those are different op amp configurations, and you are welcome to look at it so that you can see that how they build those stages and all. Next, let's look at slew rate. The slew rate is important. Why is it important? Before I get into this, let me try to say why do we even look into something like a slew rate. For that, we need to look at this plot, which we looked earlier. We said that if this op amp was used as a buffer, we applied an input which was more like a square wave pulse, which is shown here. It goes up as the input. We know the output will be, will have some sort of a settling. So this is the settling where the phase margin is not so good. Okay, it's less than 60 degrees. If it was 60 degrees, it will come and just settle down here, right? So this is the case where the settling is what we call small signal settling, is based on what the phase margin is, and in this case it's less than 60 degrees. Based on the response, I can tell that. But how about this region? Let's say we start from here, and this jump could be actually a big jump. Okay, it could be hundreds of millivolts or maybe volt. Okay, so when we start, this one goes straight up, and this is actually a large signal behavior, and that is what we call a slew rate limited. Okay, so there is a limitation on the circuitry of how fast it can go up or even down. Let's say if it was actually a negative pulse, how fast can it go down? Okay, it goes very linearly over this large range of signal swing. So it's actually a large signal behavior, and this is dependent on something we call as a slew rate. That tells you how fast can it actually slew from, say, low to high or high to low. Once it has done slewing, then only the whole concept of small signal settling, that what is my unity gain bandwidth, what is my phase margin, and how good I'm going to settle, that is what we call a small signal settling. That only kicks in after the large signal settling is over. Okay, so in this region we are not really dependent on what is my unity gain bandwidth, what is my phase margin. No. In this region we are dependent on something called a slewing, which is what I will explain here. And after the slewing has happened, after this large signal behavior has actually settled, then we go to the final settling, which is because of small signal settling. This is because of unity gain bandwidth and phase margin. Okay, so what is this slewing? So let's say, I'm showing the output stage first. There are two elements to the slewing, which I have labeled as A and B. So the first one is the output. We have a big capacitor. Anytime this node moves, right, there is a current that is needed, which and so we will have some dV by dt, okay, as what we call as the slew rate. Somebody has to charge and discharge this capacitor. If you were to charge it, M7 will charge it. But if you were to discharge it, in this specific case, since we have a constant current, which we have been calling, say, as I bias 2, right? This was implemented by the transistor M8 in our previous example, like this guy. This always carries a constant current of 628 microamperes in this example. But here I'll not use the exact numbers, I'll just use variable names like I bias 2. So this discharging, if you want to know what is the rate of discharge, dV by dt, you can take this V and write V as Q by C. Okay, Q is the rate of change of charge, and I take the C out, and if you do dQ by dt, this is nothing but current. So what is the max current that can come out of this guy? That is I bias 2. So the slew rate, which is a rate of change of voltage with time, comes to an expression of like I by C. I being the bias current and CL in this case being the load. Okay, so that will give you a slew rate when it is going down negative. Okay, so this one is when this is swinging negative, not for this positive case, but when this output will be swinging negative, it will be slowing down. Okay, if the input fell down fast, this thing is going to be slowing down. Okay, and this is one of them which will limit. This is not the only limiting factor. Okay, well, so how does it limit? You only have so much current to discharge a cap. The cap could be big. That means this discharge rate now becomes smaller and smaller. You are not able to discharge it too fast. Okay, so that behavior is called slewing. There is another cap in the circuitry which is the compensation capacitor, and when these slewing things happen, let's assume that this I bias 2 is extremely high and it can discharge this cap really fast. Okay, but what could happen is, how about this cap also has to be charged. Okay, the two ends of this thing has to be charged properly, and who charges and discharges this capacitor? Well, we can take a particular case where we have the first stage here with the tail current of I bias 1. Okay, and if this is the positive input, if the positive input is going high, let's say it is high, is the positive, yeah. So let's say if the positive input is going high like this, we crank it high really fast. Okay, then what will happen is all this current, this bias current, which normally splits into two parts, now quickly because the slewing behavior will not split into two parts. This will remain low. This node is actually attached to the ground. Right, so there is a connection from V out all the way to this point. This is the negative terminal. So it was sitting low. This output was sitting at some low voltage, and we have suddenly yanked this terminal high. Right, it was initially sitting low, so the output is low. This is also low, and we have suddenly yanked it high. If we suddenly yanked it high and this has still sitting at low, what will happen? This device is going to pull all the current to go through it. This device will go off, it will not carry any current, and all of this I bias will actually go through this. And if this device is off, is not carrying any current, that means there is no current here, right? Because it's a current mirror. So all the current that it's carrying like this will now actually come and charge up this capacitor. This is low, this is high, and it's trying to pull this node to go high, so it has to pull current this way to charge this guy up. Okay, so that charging rate, again if you do the slew rate, will depend on, which I'm calling a slew rate 2, is again I by C. C being the CC, the compensation capacitor, I being the I bias 1. Okay, so if you don't have enough bias current in the first stage and your CC is big, this is going to be slow. So we have got two capacitor charging, discharging going on, which could limit the rate of slewing. Okay, and whoever is the minimum of the two will actually determine that. Actually, I should not really write this because it is not true all the time. Yeah, I should strike this off, because this effect is happening when it is discharging from high to low, right? This effect is happening when it's charging from low to high. So it is really not happening at the same time, these two events necessarily at the same time, and that's why we should not really do this. So this we can actually call as the slewing rate when it's going from high to low. This is of a slewing rate when we are going from low to high, and these two slew rates will determine kind of how fast can you slew high and how fast can you slew low. Okay, so what happens is, as I mentioned in this example, we yanked this high, but this was sitting at low and it remained low. Right, because this point is shorted to the output. Output cannot change fast because the output is starting to charge up, but it's still far away. So that is a point where you can see this input and this input are not equal. This has gone high very fast, but this has not caught up yet. It's trying to catch up. Okay, when the slewing finishes, that is when this catches up with this guy. So these two have almost very low voltage difference. They both have equal current splitting that will start happening at that point, And when that happens, then only the gain of the op amp is higher, it has a high speed and all that. That is when the small signal settling, which is because of what is the unity gain bandwidth and what is the phase margin, that kicks in. So till that small signal thing, we were actually in a large signal behavior where actually half of the op amp was off in this input. It wasn't even getting this current, right? So it's the slewing that finally brought this node up, where the op amp actually started acting as an op amp, has high gain and everything, and then the small signal settling happens. So that is the reason why slew rate is also an important thing that you have to keep in mind while designing this, because you might have good small signal settling and everything there. You might have extremely high speeds, like 100 megahertz or even more or whatever it is, but your slewing might be dominated by this capacitor, and if it takes too long for you to slew, then that op amp is just going to have a very slow, sluggish response. So you also have to improve slewing then. Okay, so this is what we mean by the slew rate of the op amps, and hopefully you are also clear about the large signal settling and the small signal settling regions. Common mode rejection ratio, or common mode. So as we said, common mode, so what common mode means is we have this op amp, you could have these two inputs and they both could move in the same direction. So you have a differential signal is 0, but both the signals could be moving up. That is called as a common mode signal. So any differential operational amplifier is designed to actually reject common mode signals. It should be sensitive to a differential signal. It should have zero sensitivity to common mode signal. It should completely reject it. In this case, let's see what is the common mode rejection here, and from where we come at the common mode rejection ratio. But let's look at this input stage only. So this is the input stage of the op amp, M1, M2 shown, and this is the tail current source we had, which is RDS3. When you do a differential excitation, like this is going up, this is going down, what happens to this node? This node remains at an AC ground. Now we don't have a differential excitation. We are only doing common mode excitation. That is, they both are going up or they both are going down. This is not an AC ground anymore, and you can simplify this model from here to here by saying you take RDS and you split it into two RDSs this way. So the effective parallel combination is this, and of course they will also have parasitic caps, all the gate to source cap, source to bulk cap, and this, that, all kinds of caps will be there. I just club them up as some CP as a parasitic cap. Okay, so here what happens is, now if you want to look at low frequencies only, okay, let's not worry about the caps. What is the effective GM? So when we were in differential mode, this goes up, this goes down, this was AC ground. So what was the GM? The effective GM was GM1, right? That's the GM of the circuitry, because this point was AC ground. What is the GM, effective GM in common mode? Now this has become more like a source follower, right? Its source is not at ground anymore, and if your GM times 2 times RDS3 is pretty big, okay, which is GM times RDS is pretty big anyway in most of the things when we try to design it, then you can show that this effective GM would be roughly equal to 2 times RDS, or roughly equal to this resistor that is attached here, right? That's the basic fundamentals of the source follower, which I'm hoping that you know. If you don't, just go revisit a source follower and see how does the effective GM looks and gain looks and all that stuff. Okay, so here is the GM for differential mode, here is the GM for common mode. So what is the ratio of the differential mode gain versus common mode gain? That is going to be, see, the rest of the circuitry is same whether it's differential or common mode, right? The only difference is in GM. How does it convert a voltage to a current? Once you have converted to a current, the rest of the circuitry cannot distinguish at the input whether it's common mode or not. So if you take the ratio of the two GMs, that will become this, which we want to improve, and that is what is called CMRR of this circuitry, or common mode rejection ratio. Okay, so it's a product of GM and RDS. So at low frequency it is true, but at high frequency what happens, this RDS gets short by this cap. So if these devices were big, or if this devices were big, right, this device here, then they will have a lot of parasitic capacitance hanging at this node. A high capacitance at this node means that you have lower impedance. So at higher frequencies your CMRR will tend to go down, and in some applications it's very important, so you have to watch out for that. So any of the parasitic cap could kill your CMRR, so you have to watch out for that. Sometimes what people will also do is, even DC wise, if this RDS is not good enough and they want a huge amount of common mode rejection, you could actually go back and say, my current source, where is my current source? So my current source is like this, right? One. I could put another device in series and make it cascode. I could make a cascode current source if I can tolerate the headroom, like you have to have enough headroom now to do it. That will also help improve this effective value. So RDS will actually in that case become as we saw previously is GM times RDS square by cascoding it. So this is CMRR. Then next we go to the portion of the noise. This noise is actually a very, at least when I was in the school, in colleges, this was very confusing. And every time I went through this, it only confused me more. But after going to the industry and seeing that how this noise plays out and how it affects, I think I would just like to explain it in a way, hopefully, where I don't confuse you. I guess that's what I'm trying to say. So let's see if I can do a good job of explaining noise to you guys. I will try not to go into equations, because once you go into the equations of noise and all, it just gets too much complicated. Let's start with noise and say what are the kinds of noise. So we'll try to revisit it a little bit, but I'm also assuming here that you have the fundamentals about noise. You've studied them, like thermal noise and flicker noise. Okay, so let's take a simple NMOS device. Same is true for a PMOS device also. But let's take an NMOS device, and what are the two kinds of noise that we normally worry about? Thermal noise and flicker noise. What is thermal noise? Thermal noise is the noise in the channel. When a channel is formed, whether it's in active region or saturation region, it acts as a resistor, and as we know, there is always going to be some noise associated with it. Okay, so that is what we call as the thermal noise. What is the flicker noise? The flicker noise is we know that right where the channel is formed, there is a silicon dioxide on the left side, and there is a silicon with a channel, right, an N-type or a P-type, in this case an N-type channel on the right side. So silicon dioxide is on the left side, and what did I say, left or right? I don't know, but okay, left side is silicon dioxide because that's the gate, and right side is the channel. Okay, so right at the interface, when you have these two different kinds of materials, you have seen the long back in other lectures, I think we have seen that what is the silicon lattice structure? We have a certain lattice structure for the silicon, and then there cannot be an abrupt change to silicon dioxide structure, which is a different lattice structure. So when there are two different kinds of materials and two different lattice structures happen, it does happen gradually, and there is a region where there are some extra, unwanted things, like maybe extra holes or extra electrons there because of the transition in this lattice structure. They will get generated, and let's say in this case, if it was an electron that got generated in those interface traps, they also call them as interface traps. If it gets generated, that electron will come and just get swept in this channel, right? That electron did not come from the source, right? Remember, the current flow, the electrons is from source to drain. Somewhere in between we added an extra one, and that acts as a noise. That is an unwanted one that acts as a noise, or an electron going through it might even get recombined with a hole there. Right, could get in. There are interface traps, and it could get trapped, and it will not make it all the way to drain. So both cases are possible, and whenever something like that happens, this is what we call as noise. Anything unwanted is noise. Okay, so we have flicker noise also. So these are the two kinds of noises there, and if I just look at thermal noise only, there are two ways we normally like to represent it. Remember, so I will start with this first, because this is more physical. Remember, there is noise in the channel, thermal noise, because the channel is on, and we represent it as an equivalent current source. It's carrying a current. In parallel, we show a noise current whose value is roughly 4 kT some gamma times GM. GM being the transconductance, gamma depends on the process. In many cases, it's 2/3 that's being used, but this could have huge values, 2, 3, 5, who knows what. But this is all that comes from the modeling based on what these deep submicron technologies are. So I will not go into all that, because at the end, how accurate is this expression? It doesn't matter to me. It's what the simulator is going to solve. Okay. So this is the way where we can model the noise current in the channel. Now there is another way people like to do it, and this is where you take the noise current, and if you know the effective transconductance GM, you can divide it by GM square. Remember, this is not noise current, it's IN square. It is more like a power. Okay, This is more like a power. So if you do I square R, right, power, noise power, and if R was 1 ohms, then I square gives you the power across 1 ohms. So here this is showing you the noise power in a superficial 1 ohm resistance. Okay, so we always try to use it more like a power in the power levels to do this. And also this is actually the other thing is there is it is actually also a density, means it is a density, it is the noise density over frequency, because you could have different frequency components for this currents that's flowing. So if you want to know the actual noise power level, you will have to do 4 kT gamma gm times delta F. Delta F is the range of frequencies between which you're trying to integrate the noise power to get it. Okay, so this is a noise density function. Anyway, so if you have this, you can reflect it back as an equivalent noise voltage, some Vn square at the input, by dividing it by Gm square. So you will take this, because this is the current. What is the voltage to current relationship? Well, it's Gm times V is the I, right? But since we have I square, we will divide it by Gm square. So if you divide it, the Gm will just come down in the bottom. So in the current expression, it's right here. In the voltage expression, it's right here. So this is only a way to ease some calculations, as I will show later on. But a physical noise voltage does not remain at a gate. No, there is no noise on the gate. The noise is always on the channel. Just to simplify our calculations, we'll bring it to the gate, and I found that a lot of the people think that there is actually noise on the gate of the MOSFET. No, it is not. It's actually on the channel, and sometimes for simplification purposes for our calculations, we show an equivalent noise source at the gate. So that's I hope you understand that part, that we are actually deriving this model from this model. So this is thermal noise. Flicker noise. Flicker noise has much more complicated equations. It is based on interface traps, the silicon dioxide interface. They're best modeled in the simulator rather than me trying to write an expression here. But the only rule that applies to flicker noise is, if you have a device and it has some flicker noise that you're getting from the simulator, the only way to reduce the flicker noise is to increase its W and L. Flicker noise is inversely proportional to the area of the gate. If you increase its W or increase its L or both, it will only lower the flicker noise, and that is the only thing, pretty much the only thing you can do in a design. Once you find out that you're simulating and you find, oh, my flicker noise is too high, what can I do? Well, you just have to increase the W and L of the gate to actually lower it. Sometimes what you can do is, let's say if you have a choice of NMOS versus PMOS, PMOS tends to have lower flicker noise compared to NMOS. But let's say if you can't just change the topology directly, you have to use an NMOS or you have to use a PMOS only, then what can you do? You can just simply change the area to improve the flicker noise. Another thing with the noise that happens, and since we're going to talk about the op-amp here, is there is an input terminal, there's an output terminal. Where you have all the noise from all these elements, you can take it all the way to the output and say this is my total output noise. Or you can also divide it by the gain, like the AV square, okay, AV square, and put it at the input and say this is at the input. Both of them are fine. I myself use the input referred noise more. A lot of the people use the input referred noise. Even though this is not a physical noise, the noise is always at the output. You're dividing it by the gain, and then you're representing an equivalent noise that would be there at the input. It just helps with some calculation. So we will just use this topology here. Especially since I come from the RF background, a lot of the noise calculations we try to do, we'll always bring it to the input and try to define things like noise figure and stuff like that. So we'll use this here. So let's see. Let's take this structure that we had and how can we derive noise for this structure. So here is the differential input pair, the tail current source, the PMOS devices, and this is the output stage. I am not showing the biasing here. I'm going to make an assumption that this point is AC ground. Okay, even though it is not actually AC ground, but still we'll make an assumption that this is going to be AC ground. Okay, somebody's at the door, so I'll be back in just a few seconds. Excuse me, please. Yeah, I'm back. Sorry, somebody at the door. So let's look at the noise and see what are so these are the different elements. As I was saying, I'll make an assumption that this point is AC ground. Even though you have noise from the bias circuitry and all can come here, but for simplification purposes, let's keep it AC ground. Normally we try to sometimes put, big capacitors here to make it AC ground. So let's not worry about it. Okay, so let's start picking up devices. Okay, since it's a small signal type, noise is a small signal type analysis, we can add each of them in a certain fashion, which is mean square. So we'll look at it. Let's start with M1 and M2. They are equal. So there is a thermal noise and flicker noise, and I will combine it as a single noise, and I will also reflect it back at the input of these devices. Okay, so this is a superficial noise, so not a real one, but all the noise that was in the channel, I have reflected it back as we talked about here. Okay, so this could be kind of the noise that is there. These two noise sources which come at the input will add directly to this one. What we are trying to find out is this: what is the total noise at the input? What is this VNI square at the input? What is this value? So these two will add up directly. Okay, so VN1 square plus VN2 square. Let's look at M3. Since M3 is close by, let's look at what happens. This has a noise in the channel, so it will create a noise current. But what happens to the noise current is this noise current will split equally on both sides. Right? If both the sides are completely symmetrical and matched, and that's what we're going to assume, it will split equally on both sides. That means what goes out finally at the output is going to be 0. So let's say if you have IN3 square here, half of it goes here, right, this way, coming down. Here it's coming down. Here also half of it coming down. So the one coming down is same as the one here. So what goes out is nothing. So this noise, because of this being a common mode type of noise, it gets cancelled by this differential circuitry based on the assumption that we have perfectly matched left and right side, but that's not going to happen all the time. Okay, so some of it will show up based on mismatches and all, but for now we can assume that this noise does not show up at the output. Okay, so we don't have to worry about this noise source. Okay, let's see what happens M5 and M6, the PMOS devices. Again, I can start with the assumption that the channel noise, I will show it as an equivalent voltage square noise at the gate. Okay, so you can do that, or you can also show the channel noise whichever way you want. But if you have this will actually get, so will this noise show up? First of all, of course, yes. Let's look at C6 here. This will show up directly as a current noise at the output here, and it will be multiplied by all the RDS that you have here to give you the noise voltage here. Noise voltage or noise voltage square, whatever you say, and once it's there, then it will be amplified by M7, it will go out. Okay, so it will have it. But how much will be there? So what is the conversion of voltage to current here? That is dependent on GM of this PMOS device, right? GM6. If this is the current, what you can also say is, let's say I know this current flowing here, I want to reflect it back to this input. I can take it to the output, divide by gain, but I can also let this noise current flow, which is in M6, I can let it flow through M2, okay, and then I want to reflect it back at this input. How would that be? That would be, let's say if you took this 6, okay, VN6 square, that multiplied by GM6, in this case is GM5 and 6 are the same, square of that will convert it from voltage to current. So this voltage to current is given by this term multiplied by the GM square. Okay, then as this current is flowing here and I want to bring it back to the input, okay, and when I'm doing it, you might be getting confused. How come you have noise voltage here and here? You got two currents here. No, when we do this kind of an analysis, we only pick one at a time, assuming everything else is 0. So this is 0, there is no input here. Okay, so only one of them is there. So as I said, this voltage to current is given by this term here, but I also have divided by GM1 square, because what is happening is this current, if you convert it back to a voltage, you have to divide it by the transconductance of the stage, GM1 being GM2. So that's why and they both will actually, if you work it out, you'll see they both will show up equally. Okay, whether it's from this guy till here or this guy till here, it's all the same. So 5 and 6, their noises will show up, but with a ratio. And this ratio is important. for you to understand that it is a ratio of the GM of the PMOS to GM of the NMOS. If the GM of the PMOS and the GM of the NMOS are equal, we just did a design example earlier where the GMs were equal. What that means is the noise from these two guys will also show up equally as the NMOS input devices. Okay, so that could be actually a lot of noise, and in many of the examples, what we do is if you have to design it for lower noise, we want to make this GM actually lower. The GM of the PMOS, we want it lower than the NMOS. So this term is actually small. We are mainly dominated by this input term. We'll do things to make them bigger size, increase current and all that, but we want these input devices to be the dominant source of noise here. We don't want these PMOSs to be equally dominant, and to achieve that goal, we will reduce the GM of the PMOS device compared to the NMOS. Not like what we had in the design example, GM of the PMOS and NMOS were equal. Well, I guess I will not go back, right, but you can go and check at it. Okay, so this is there. So we looked at these 4 devices, and we see that these 4 devices do contribute to significant amount of noise, and we want to look at this ratio of GM of P to M. This does not, because this appears as a common mode noise. How about these devices? See, the noise, they also have noise, but now if I'm trying to take this noise and bring it all the way to the input, I will divide these by the voltage gain of the first stage, right? Right now, if there is any noise here because of M7, which is this, I will divide it by voltage gain square of the first stage. Sorry, not voltage gain, but voltage gain square. So all this gets suppressed heavily by the gain here, so we don't really have to worry about these noise so much, whether it's M7 or M8. Why? Because there is huge gain in this first stage. So that suppresses the noise. So at the end, the major noise contributors here become the input devices. All of its noise shows up at the input, and also these PMOS load devices, a fraction of them will show up at the input based on what is the ratio of GM of the PMOS to the NMOS. Okay, so that's how the noise actually gets contributed by various elements in this op-amp, and that becomes a noise. So if you're trying to design a low noise op-amp, okay, and as we will show, noise is similar to offset, low offset op-amp or low noise op-amp, you know which devices to stress on and improve the design. Now, how to reduce noise, as I said, is I want to make this GM lower. So one way to make GM lower is, GM is 2 times I by V on. Try to make V on higher. That is VGS minus VT. If you design them with bigger VGS minus VTs for the same current, their GM will be lower. That's one way you can do it, but anytime you have more V on, remember this voltage is VT plus V on. That actually will squeeze your VDS. Okay, so you might run into headroom issues, because anytime you increase V on this guy, its VDS decreases. So you have to see whether you have headroom to do it or not. That's one way, if headroom issues allow you. The second way is, what we also do a lot in the industry, especially for low voltage designs, is we will do source degeneration. So we will take the sources and we will degenerate with resistor, and since we are trying to lower the effective GM of this PMOS, right? So the effective GM for this source follower, this acts as a source follower, that becomes GM by 1 plus GMR, right? And if GMR you can make it big, let's say 10 or something like that, then your effective resistance becomes 1 over R. So we have eliminated all the noise from these PMOS devices, but the noise from the resistors will come now. That is what will be causing noise. And most of the time you will find, as you start doing lots more and more design, is a MOS transistor always causes more noise compared to a resistor, whether it's thermal noise or it's flicker noise. Especially the flicker is horrible in many of these submicron technologies. But any day if I had a choice to pick between, would I like, from a noise perspective, would I want a resistor or would I want a MOS? I will always pick a resistor, because a resistor will give you less noise compared to a MOSFET. So here also you have to have extra headroom now, because you have an IR drop. So this is also buying into your headroom, but they both will bite into the headroom, but based on which one works better for you, you can do tricks like this to reduce the noise. Okay, the last section that we have is in this particular lecture is the offset voltage, and offset voltage actually is comes out because of mismatches, and it is similar to what we have. It's like low frequency noise or DC noise. So if you have noise, as we did here, right? If we consider them to be DC or low frequencies, everything we did here, all these expressions are going to be true for offset also. So offset arises mainly because of matching between various devices. So this is a differential pair. What we have been talking about is the left side is exactly equal to right side. If I take just this diff pair M1 and M2, they are not going to be exactly equal. When we fabricate it, we do all kinds of things in the layout to match them so that they are exactly, but they will never be exactly. There is always going to be some small finite amount of mismatch that will be there. Okay, so typically the way we represent the mismatch between two of them is with a percentage mismatch. The percentage mismatch between two is given as something like a sigma by square root of the area. So you have a W and L of these devices. If you take a square root of the area of the gate and you put a sigma, sigma is more like a number that you get from the foundry. Okay, it could be say 1% or something like that. It could be less than 1% for certain good processes, or it could be higher for smaller geometry, so, like the submicron processes. So this is a number that you get from there, and you use it to see what kind of percentage mismatch can I expect between these two. Let's take an example. We did the design where we said M1, M2 was 25 micron by 1 micron, right? So we could do, and if sigma was 1%, which is from the foundry, from the fabrication, so percentage mismatch between these two can be computed as 1% by square root of the area, which comes to roughly 0.2%. Okay. Now, what are the two different kinds of mismatches that could happen here? First of all, when we are doping, right, we are creating a certain VT, they have some threshold voltage. There could be a mismatch in their threshold voltage itself, which is what I'm showing here on the left side as VT mismatch. Then there is going to be W over L mismatch. They are not going to be exactly same 25 by 1. There is going to be some mismatch there too. Let us assume that for both these cases the sigma is 1%. Some cases, the sigma for VT mismatch will be different from W over L mismatch, but for now I'll just assume that they are the same. So through this calculation we show that there is a percentage mismatch of about 0.2%, okay, between two. So first let's say VT mismatch. How much mismatch in VT can we expect? If the nominal VT is about 500 millivolts, then the VT mismatch of 0.2% could be about 1 millivolt. So if you look at the VT of M1 and M2, right, they could be off by plus minus 1 millivolt, and this is a 1 sigma number. We have these things called 1 sigma, 3 sigma and all. The statistical, I will not go into this, but this is just a 1 sigma number of say 1 millivolt. Okay. Now, how about what happens when you have W over L mismatches? Okay. So when you have W over L mismatches, you can assume that, let's assume that the VTs match perfectly. But because we have W over L mismatch, the V on numbers are going to be different, right? The VGS minus VT, the V on number. So what is the V on number? V on number is 2 times the drain current by K prime W over L. And let's say if this V on number was 200 millivolts, we design it for 200 millivolts. What is 0.2% mismatch, which is from here, of 200 millivolts? Okay, why did I have, oh, okay, I see. Yeah, it's a 0.1%, not 0.2%, because W over L, if it has 0.2%, when you take a square root, it becomes roughly 1 by 2 of that, right? So 0.2% will become 0.1%. That's of V on is roughly 0.2 millivolt. Okay, so we are getting these two numbers. If we had VT mismatch, that would be in the order of roughly 1 millivolt, 1 sigma number. If we didn't have VT mismatch and we only had W over L mismatches, it will give you about 0.2 millivolt in V on. So what is VGS? VGS is VT plus V on, but what happens is we can't just simply add it like that. These two are uncorrelated events, This is not going to happen all the time when this happens, or vice versa. So anytime we go to noise, as we do noise addition, we'll do a mean square addition. So we'll take a mean square value for this and a mean square, and this, in this case, if you just want delta VGS, that you do a square root, and that will come to about 1.02 millivolt, or roughly equal to just this number, right? So we could have an offset up to the mismatch between them of up to this could be plus or it could be minus. So if you take the range of it could be up to 2.02 millivolt, but this is a 1 sigma number. I'm talking about the range here. And if you talk about 3 sigma numbers, you just have to make it 3 times. So this is how we would calculate it, because it's just because of a single pair here. You can extend the same calculations as we did and divide it by the GMs and all for this pair also, based on the W and L of these PMOS devices. And that's how you would calculate or do an approximate calculation of the offset and come up with a number, 1 sigma number or a 3 sigma number, and then see, is it too big? See, all this calculations is giving you a number, but then after that you just have to ask the simple question, is it good enough or not? If the answer is no, this is too high, then what can you do? There's only one thing you can do. You cannot control the foundry, right? Those mismatch numbers. That is what the fabrication does, and you cannot change the fabrication there unless you have your own fab. Most companies don't have their own fab. What you can change is you can make the area bigger. You have to increase your W and L. So as I said previously, is for flicker noise, the only thing you can do is increase your area, increase your W and L. Same thing for this kind of offset. You have to increase your area, you have to increase your W and L to reduce your offset voltage if you need to. So this will only give you an estimate of what the offset voltage is. But finally, when you have the whole op-amp design, right, like with this design, and you put these numbers in there, in the simulator you can run something called Monte Carlo analysis, and that will actually give you, it will apply mismatches to different devices in that Monte Carlo analysis, and it will give you what the offset voltage is going to look like. It will give you a good distribution, and from there you can find what is my offset voltage at the input or output, whichever you want to call it. In this case specifically, it's the input, differential input, and it will give you a nice distribution of the offset voltage. So that's with the offset voltage, and we'll conclude this lecture here, but we'll pick up again next time for more on op-amps. So let's also look at something called power supply rejection, or PSRR. PSRR stands for power supply rejection ratio. This is actually a measure of if there is some noise, some unwanted signal, some garbage on the power supply, which is our VDD, then what is the capability, or what is the ability of this op-amp to reject this garbage from passing it to the output? That ability to reject it is called power supply rejection ratio, and that becomes important because all these times we have been assuming the VDD as AC ground, as a clean supply. It is actually not true. When you make actual ICs, you could have many ICs sitting on a PCB, and they would always cause various kinds of interference, various kinds of noise, various kinds of switching at the VDDs of one another. So there is always noise there. So how can this circuitry actually suppress this noise? That ability is called PSRR, and higher the PSRR, the better it is. We want these guys to be able to suppress this noise. Noise not only comes from the supply, the VDD pin, it also comes from the ground pin. I have not shown the ground pin here, but noise could also couple from the ground, and what would be its ability to suppress that noise? That is what we call as negative PSRR. Negative PSRR because it's coming from the ground side. This is more like a positive PSRR. And if you refer to Dr. Allen's book, which I mentioned earlier in one of the lectures, which is the CMOS analog circuit design book by Allen and Holberg, he has a very good detailed analysis of both positive PSRR and negative PSRR in the op-amp chapter. So you will be able to get a lot of good a lot of details with small signal model derivations, understanding what is going on, all that stuff there. But here my goal here is to look at this more from a qualitative point of view. I don't want to stretch it too much by doing all the derivations, but I just want to see if you would qualitatively understand what goes on in the circuitry and try to come up with a qualitative explanation of the PSRR plot, and we will only look at the positive PSRR. One of the other reasons I'm only looking at the positive PSRR, which is only VDD but not the ground pin, because most of the times when you make a circuitry, a lot of the blocks have they could get independent grounds. So the probability of injecting more noise at the ground, that probability is actually lower than the probability of injecting noise at the VDD pin. Okay, that's what is also true in many of these RF analog type circuits. That's why I will only focus mostly on the positive PSRR and try to come up with an intuitive explanation of what goes on specifically to this op-amp. So here is the op-amp structure that we have looked at. So I've tried to redraw it. I have gotten rid of all the biasing and everything here and represent the tail current source with a simple RDS. Here is the differential input pair. When you're trying to inject something on the supply and you want to know how much of it is coming to the output, you're automatically making an assumption that the inputs are AC ground. Not both of them will be AC ground. This is a mistake on my part. This is the positive input, will be AC ground, but the negative input actually is connected to the output. So this would actually be connected to the output here. Let's see what else. And this is the output stage with its compensation and everything that is there. So let's try to see, first of all, what happens when we apply a voltage, say Vx at this point. Can we get some kind of an intuitive understanding into this circuitry without drawing the small signal model? So if you apply a Vx to this point, we know that this is the output state. So first of all, this is Vx. Yeah, right. So the source is Vx. The gate I don't know yet. Let's neglect this AC ground for now. Okay, so at extremely low frequencies, if I wanted to know, I don't know what this voltage is at this point. So I don't know VGS, and if I don't know VGS, I cannot find what the current here is. Okay, so just starting from here and looking at the output will not give me an answer directly. I have to go back and try to find out what is happening at this node here. So let's look at this node. Okay, so we have applied a Vx here, which is applied to both these devices. We will also assume that these are exactly matched, exactly symmetrical, no mismatches at all. What does this look like? This looks like a low impedance point, which is 1 over GM. What is the impedance from the source of this M3 device to the drain of an M3 device? Any diode connected device, if you solve it, you will see it's 1 over GM. So here we look at 1 over GM. Where do we look down? Looking down, if we assume that these are AC grounds, this is not necessarily AC ground because here is the output here. But if we assume that Vx is going to get attenuated big time by the time it goes to the output, then this point is like AC ground, and this is also like AC ground. This is the positive input, it's AC ground anyway. Negative input is attached to the output, but I will make an assumption that it's very small. We are hoping that this circuit actually has very good PSRR. So none of that Vx goes up to the output, so we can still make an assumption that okay, it's AC ground. What that does is then it makes this thing looks just like an RDS, right? Because this is an RDS here, there is no way we can get any voltage here, and this tends to look just like the RDS resistor that we have. So looking down at this point, if I go back to this point again and say what is the voltage here? Looking down, we are seeing RDS plus all these effects will come, because see, RDS, and at the end of RDS is not AC ground. It's going to be further, maybe 2 RDS 3 or something like that will get added to it in series. So the bottom line is looking down, it's high impedance. Looking up, it's low impedance. Low impedance because it's 1 over GM. Okay, so if you apply a Vx across a resistive divider circuitry, most of the Vx is going to show up here. Because this is low impedance, this thing looking down is high impedance. That's why I've written this annotation here which says this voltage is going to be roughly equal to the same as Vx. Okay, roughly equal to that. So if this is Vx here, gate, what is the VGS across this device? The VGS across this device roughly becomes 0, right? This VGS is 0 as well as this is 0. So these two branches, they are not able to create any current, any small signal current, if the voltage here, the VDD moved by Vx. That is what is the first observation because of this connection here. Okay, so if it is not able to create any current, what happens to this node? Right, there is no current that's able to go and charge up these RDS values. This remains as AC, kind of AC ground, right? So it is not able to create any current, but see, there is another resistor here. Yeah, I should not say it's AC ground exactly. It will have some voltage. And why will it have a voltage? Because remember, this M4 has an RDS also there, right? So if it cannot create an AC ground, it still has an RDS4 that is attached between these 2 points, and then we will have RDS2 plus this RDS effect that will come here. This will become more like a cascoding looking down. If you remember, we did the CMRR analysis where we said we have one device and then we have another device here. So this would look like a big impedance looking down. Okay, we still have RDS, so there will be some voltage of Vx that will come here, a small value. Whatever it is, we can derive it, but that's not the goal. That's not my goal here in this analysis here. We are trying to see how can we qualitatively find a simple answer. So there will be some DC. It's not AC ground. This AC ground I drew it mainly for a little higher frequency, and I'll come and explain that. But for DC wise, so this is not going to be exactly AC ground, but it will have some value which is going to be smaller than Vx. And if we say that, okay, that is very small compared to Vx, we can make an assumption that VGS here, okay, is going to be completely equal to Vx. We know the source here is Vx. The gate we were trying to find out, we kind of came to a point intuitively which shows like this is going to be a value, it's going to be a small value, and we don't need to worry about it, that it's going to be anything comparable to Vx, so we'll just assume it to be a small value, and that creates a current here, right? Is low frequency wise. So the current here is going to be GM times, this is the GM times Vx roughly. Okay, it will create a current. If it creates a current, this comes here, then what is the, so this is the point that I'm trying to make here is, so M7, if with our assumptions, if the gate is at AC ground, what is the gain from source to drain of this device? That would be GM7 times the total RDS. Looking here, RDS is of RDS7 and RDS8. Okay, so we're going to get this. This will be the gain Vx from Vx node to the output point. Okay, so this is the gain that we will see through it. But then what will happen is, if we go and further say this op-amp is actually in closed loop, right? We might have gain from Vx point to the output, but because it's in feedback, the loop gain of this closed loop configuration will suppress that. So what that means is, even though this is the open loop gain, this has to be divided by the closed loop gain of the op-amp. Okay, I mean not the closed loop gain, the open loop gain of the op-amp, because this is in a closed loop configuration. So let's see what goes on here. So this plot here is a similar plot that we have been looking at. So I tried to reproduce it and say, here is the gain at low frequency. The gain is pretty high. Then we encounter the first pole, then the gain tends to go down. It crosses the 0 dB point, which is the unity gain bandwidth point, and then it keeps going down, and hopefully all this, it has got good phase margin and all, so we don't have to worry about the stability part of it. So if this is my gain, okay, so this tells me the gain from Vx to Vout. And this op-amp is also in a feedback. So feedback series says that you have to divide that gain by the total loop gain of this, right? And the loop gain of this is basically nothing but AV times the feedback factor is 1. So this will actually, you will take this gain and divide it by this response that we have here. So even though there is gain from the VDD to the output point, we don't see a gain, because this op-amp in a feedback configuration, its own gain, the total loop gain of this closed loop system, is going to come and suppress it. So what will the PSRR roughly look like? It will, at DC, it will have some negative value, negative in the sense that I'm talking about dB scale here. Okay, so if you have something like this 0.001, that is actually minus 60 dB. 20 times log of 0.001 is minus 60 dB. So you take this gain number divided by the open loop gain, that will give you some negative number. So this is where the PSRR will start at. This plot is PSRR, which is a measure of V out to Vx. How much of the Vx actually shows up the output. Since the op-amp has pretty good gain here, it suppresses it pretty good. Then as the op-amp's gain decreases, right, this feedback loop is losing its capability to suppress this leaking through here. So the PSRR will also show an exactly opposite characteristic. So whatever the open loop gain of the op-amp looks like, PSRR will look exactly opposite of that. And at around unity gain frequency, this will run out of steam. There is no feedback at all. Then what will happen is it will just pretty much lose steam, and certain things happen here, like where is the location of the second pole. This is a region where intuitively I can't explain exactly that where does it turn around and where does it start to go down again. This part is actually more explained by a more detailed small signal analysis, which is what Dr. Allen's book has. So I would encourage you to look at it if possible, or maybe some other textbooks, or even derive it yourself. But intuitively what we can actually derive here is whatever is the open loop gain characteristic of the op-amp, PSRR will look exactly inverted, like a mirror image. Then it will lose steam after unity gain bandwidth, and then after that it will turn around, then it will start to go down. And at higher frequencies, why does it go down? It goes down because of I'm trying to take this output stage here, and I'm trying to redraw it again as this way. Okay, so what is happening is I've attached Vx, and this is the output stage where the compensation cap is shorted out. So what is the impedance? If it's a diode connected device, we know that the output becomes a diode connected device. If it becomes a diode connected device, this becomes a low impedance. This becomes the CL, right? Which is actually becoming more lower and lower impedance as you go to high frequencies. So this becomes more like if you take this as a voltage divider, what will be the output? The transfer function from Vx to Vout. It will just keep going down because it's the capacitive impedance that is getting lower and lower, so the output voltage is also getting lower and lower. So this roll off is caused by that this is finally shorted as a low impedance node, and this keeps going down. That is one thing. What I don't have it here, and I should have put it, is if you keep going down, finally it would even become flat. Okay, why would it become flat? It becomes flat because there is a capacitive value from Vx to Vout, right? If I refer to this, it will just be the CGS mainly. So there is a CGS value plus maybe other parasitics, which is there between Vx to Vout. Then we have this big CL from Vout to ground. So this becomes a capacitor divider circuit. So whenever we have a capacitor divider circuit, it will have a fixed. So if the capacitive impedances start dominating, like this is 1 over GM, but if the CGS starts dominating at extremely high frequencies where 1 over omega CGS is much smaller than 1 over GM, then 1 over GM is shunted by this parallel capacitor, right? So at those high frequencies, it becomes a capacitor divider circuit, and the PSRR or the gain will become, flat. It'll flatten out this way. So that is one of the things which I just thought about it now, that I had not actually put in this node, but this needs to be extended and it will become kind of flat because at very high frequencies it just becomes like a capacitor divider type circuit. Okay, so this hopefully gives you some idea about power supply rejection and how we can intuitively solve some of it. Not all of it can be solved. We do need some detailed derivations, which I have not done here, so I would encourage you to look at those and derive those derivations to see how you can come up with a plot. But at the end you will get a PSRR plot which looks more like this, and also of course flattening out the region that I missed here. Okay, so this is important because, so what does all this mean at the end? If you have a PSRR plot for this op-amp, and if you're told that, hey, this is a PSRR, this is the specification for the PSRR that I need. I could have noise, low frequency noise, and I want it suppressed by so many dBs. I could also have high frequency noise to certain high frequency value, maybe a megahertz, maybe less than a megahertz, maybe 10 megahertz, maybe 100 megahertz, whatever it is. You have to know how much do you need to suppress the noise over frequency. Based on that, you can derive your specification that, okay, this is the PSRR that I need for this op-amp to have. If you know that, then you will know what kind of curve you want to meet. Okay, we design an op-amp with about, is in the previous example, 100 megahertz bandwidth, and we have a plot like this. Is that good enough to get this PSRR plot? Maybe not. Maybe you will need to burn more current to extend the bandwidth. Or maybe that, okay, now the bandwidth is good enough and the characteristics are good enough and it has enough gain, it doesn't lose gain, and it has enough gain to suppress the noise from the power supply. So you have to know what is your requirement, and then you have to see the op-amp that you have designed, does it meet your power supply requirements or not. So that's the key thing at the end that you have to do, and if it doesn't, what are the things you can change? You have to look into that. So hopefully now this gives you some idea about the power supply rejection. After this, I think we have covered most of the stuff with the op-amps in terms of common mode rejection, power supply rejection, noise, offset voltage, and all that stuff. I thought that this is something that I have kind of experienced myself over years of, we design an op-amp, we only focus on its open loop characteristic, but it's not just open loop that matters at the end, because the op-amp is always going to put in a feedback system. Okay, then how do this open loop characteristics changes, or how we need to look more at a closed loop characteristics, closed loop feedback characteristics. Okay, that is what is important. So let me try to give you some examples, and I think it will become more clear of what I mean here. So let's start with this example. This is what we have been looking at. So we have, this is a voltage buffer where it is connected in a follower configuration. So the feedback factor is completely 1. If you have an open loop characteristic of the op-amp like this, where we have a unity gain bandwidth and the other pole is hopefully further out, so we have got good enough phase margin, then what would the closed loop characteristic look like? So this characteristic does not tell me a transfer function of V out divided by V in. This only tells me the transfer function of the op-amp itself. Okay, this is independent of whether we have this feedback connected this way or not. So it doesn't really tell me this transfer from input to output. How do we find that? Okay, that is sometimes important, you have to find. So I'll start with this example and go to other examples where it will become more clear. So let's see the feedback system. Okay, so if you go back and revisit your feedback system theory, where we have some input to output and there is feedback. So A tells you the forward gain or the open loop gain, and F is the feedback factor, and based on that, if you derive the total transfer function, some Ts, that is equal to A as a function of S divided by 1 plus A times F. And this term A times F is what we call as loop gain. And this loop gain is very, very important, because all the stability analysis and all that we will do is pretty much done on the loop gain. You know, there is a lot of, in the control theory, you must have also studied something of some amount of root locus and all that. That is also applied on the loop gain. So what is this loop gain term? Where are its poles and zeros, and also based on those things you would apply your stability criteria and all those stuff. So anyway, so coming back here, okay, so in this particular configuration, if we want to know what is the transfer function that will look like from V in to V out, where feedback factor is 1, what is the open loop transfer function of the op-amp we have? The open loop transfer function of the op-amp, which we just showed here, right? So this is the plot we have been looking at, but if you want to write an equation for it, it would be something like AV0, that gives you the DC gain, and here are the two poles, P1 and P2, right? Now from here, if this is the open loop transfer function, we want to derive closed loop transfer function. What will be the closed loop transfer function? It will be the open loop transfer function divided by 1 plus the loop gain, where F is equal to 1, right? So if I put those values here, I will come to an expression like this. So this is my transfer function from input to output. And what does this mean? The first look at this equation tells me I cannot interpret this. I don't even know what it shows. I know the op-amp, just AVS. That open loop transfer function is like this. That's what we have been looking at all this time, right? And we have been talking about again and again, but now I've got this transfer function whose head and tail I can't figure it out. What does it mean? Well, one thing I can make up directly is, and sometimes when you do these derivations, we are human, so we are prone to errors. I always check what is my gain at DC or T as 0. Okay, so from here the gain at DC is 1, so that is good. I know that the input to output, the gain has to be 1, so at least I did not make a mistake there. Now, in this transfer function, rather than trying to expand it and get into all these things, what I thought of doing is, and which is what makes sense at the end, is remember what we're trying to do is we want to know the transfer function from input to output. We know at low frequencies it will be 1, but at high frequencies, what is it going to be? How is it going to behave when we go to, say, unity gain bandwidths, or even further out, or even before that, right? That's what I want to plot. So what I do is I take this transfer function and I normalize it into a very generic second order transfer function. Okay, so what I'm showing here is a generic second order transfer function where we have the zeta. Zeta is the damping factor, and omega n is the undamped natural frequency. Okay, I don't know what I have written here, but it's the undamped natural frequency here. Okay, and you can, if you expand this thing, it will come into a form like this. You can find what the zeta is, what the omega and all, but I'm not going to expand it and show what does each of them show for. Why I'm trying to do this is because I want to go through a few things first and then come to the closed loop. So we're going to come to this closed loop transfer function here. This is what I want to come to, but before going there, I want to revisit a few things. We know that if you have two poles, this is going to form, so at the end it's going to come and become a second order transfer function. Okay, so what are the different cases we can have? So let's say if I want to plot the poles. Okay, this is the real axis, the sigma, and the j omega axis, and let's take the first case where the poles are like this, P1, P2, like we have, right? So we have got the first pole P1 and the second pole is P2 for this open loop. If I do this, then I know that this is the case where zeta has to be greater than 1, and this is typically what we call as an overdamped system, and this is also the case where the phase margin is actually pretty good. Then what happens is, as you know from the root locus theory, that if these poles move towards each other, right, as they come closer to each other, at zeta equal to 1, they will be right on top of each other. P1 will be equal to P2. This is the condition which we call as the critically damped system. That means both the poles are equal. Well, we never want this for the op-amp, so I am not showing this to tell you that this happens in an op-amp. No, the op-amps, we always want the P1 and P2 to be far away to get the good phase margin, but I'm just showing you here all the possible cases, and this is the case for zeta equal to 1, and the phase margin will be horrible here. You know, it would have gone down significantly. You can further go down from critically damped system to an underdamped system where the poles actually now split and zeta becomes less than 1, and they would actually split and go into, you know, they will have a real part and also they will have a j omega part. So when that happens, the phase margin is worse and we end up with a lot of ringings that happen. Right, the rings are becoming more and more, and further out, if zeta became zero, that means this has got the lowest of zero phase margin. This is an oscillator now, because the poles are actually P1 and P2. They are on the j omega axis. They're not. There is nothing on the real axis. So if there is nothing on the real axis, there is nothing to damp out any oscillation. So this is a pure oscillator. So have got absolutely no phase margin. So these are the four cases that could happen because of zeta. And what is zeta? Depending on zeta is going to depend on these locations of poles. So we have not derived it, but I'm just trying to give you an overview of how the phase margin degrades going from this case all the way to this case. A degradation of phase margin could cause the poles to move this way and eventually cause problems. So let's see how we can say that, okay, we know the expression for the closed loop transfer function, V into V out for this follower. We know the open loop transfer function, which is this, you know, this plot that I have here is the open loop transfer function. This point is the unity gain bandwidth. This is the P1 and P2, all is there. So what will the closed loop look like? The closed loop could look something like, I have only got two cases here. Okay, there is a green one and there is a red one where it peaks up. Okay, so if I look at input to output, and I had very good phase margin, okay, which also correspond to the effective, this will fall in the case where zeta is actually bigger than 1, and which is the case here, right? Then I would get a really nice response which says the gain is 0 dB, and then it will roll down, so it will go almost up to the unity gain bandwidth, and then it will start rolling down and catch up with the open loop characteristics of the op-amp that is there. So here is the open loop characteristics, and this is actually the actual transfer function from V into V out. So I hope you understand that just finding the open loop characteristic of the op-amp is not enough. What is the actual input to output transfer function it's implementing, you also have to look into that. Okay, so since it's a follower, we know it's 0 dB and it goes down this way, and this green case, as I said, is where we have phase margin is really good. Now what happens is when the phase margin is not so good, let's say we were trying to design it, but we could not keep the phase margin really good, and the phase margin is somewhere maybe 40 degrees, 30 degrees or something like that. For those cases, what happens is you would see this red plot where they will be peaking. So low frequencies, the transfer function, the gain should be 1 and you're seeing 1. But then as you come towards the unity gain frequency, you would actually see it peak up. And this peaking happens because of the phase margin is not so good, or also saying the zeta is less. Okay, so this becomes a good, more like an overdamped type system. This will become more like a underdamped type system, and this will cause you a peaking. So more peaking means, if you looked at the transient response, if you hit it with a transient pulse, it would actually give you more and more oscillations, and it will take longer to settle down. That would be with this red plot. Good phase margin, which is this green plot, will mean that it will not have ringing, so it will just go up and settle down like an RC type settling, you know, without any peakings and ringings and all that stuff. So at the end, if you put it in a simulator and looked at the transfer function from input to output, you would see one of these two kinds of plots, either the green plot or the red plot. And that is coming based on whether the phase margin is good or is it not good. So this is a case what I wanted to stress here is, in most of the time we always just look at this open loop transfer function, but I really never thought about, okay, this is just of the op-amp. What is the input to output transfer function? How would it look based on the open loop transfer function of the op-amp? That is the goal that I'm trying to do here, so you guys can also start thinking about it and go through a few examples. This follower was just the first example, okay, to look at it, and hopefully with all these pictures here I did not confuse you. This was more to go back and just revisit it. Okay, so what happens as the poles move and zeta becomes less and the phase margin decreases. So, but this is what happens ultimately, is you would either get peaking or not peaking based on, you know, how good your phase margin and all is to start with for the open loop. So this was one example. Another example that I will go through, the second example, is of an inverting amplifier, and this is where I think it will start getting more and more interesting. So this is where I'm trying to show an inverting amplifier where we have V in and V out here, and these are two equal resistors. Let's say they don't have to be equal, you know, they could be in any ratio which will give you the gain, but I've just kept them equal to get a very simple transfer function, which is V out is minus times V in. Okay, and the positive input is normally it's AC ground because it's a DC, you know, at some fixed DC voltage here. So the first thing we will do is, okay, this is an op-amp. We already know its open loop characteristics, which is shown right here. We have been drawing it again and again, but now what I want to know is, I want to know V into V out transfer function. How would it look over frequency? So the first thing we will do is, as we have been doing, is we will try to know what is the feedback factor, right? And then find out what is the loop gain. This is the A. So as we did here, we have A and F. A is the open loop transfer function of the op-amp. We already have F. F is the part that we want to find out in this particular inverting amplifier case. So for that, I will redraw the circuit, and this point here, so output goes through an R, another R to say AC ground, because I'm trying to just find a feedback factor now, and this point is fed here. So if I break the loop, this part will give me the feedback factor, and the feedback factor from here you can see is it's a simple resistor divider, right? So if R and R, again if the R's are different, it would just be a different value, but here it's just half. What is the voltage here? So if you have a voltage, say some V out here, what is this voltage here? That would be R divided by 2R, right, which is half. If this R values were different, this will have a different value, right? So we have found the feedback factor for this circuitry is half. Now at the input you will also have a lot of input capacitance of the op-amp that we have not talked about. For now we'll just assume that we're just going to neglect it for these analysis. We don't want to bring in another pole and cause it will have an effect, but for now we'll just simplify it and say we will be ignoring it for now. What that means is this feedback factor in this example is half for all the frequencies. Low frequency all the way to high frequencies, I will simply assume it because that makes it easier for me to draw these plots. Okay, that's why I'm making that assumption here. So what is the loop gain then? So the loop gain, which is A times F, F is being half, so it basically becomes half, right? Whatever the open loop characteristic for the op-amp was, now it has become half. So that loop gain in the feedback loop, that determines how this guy is going to settle. Is this guy stable, unstable, whatever it is, right? It is not the open loop characteristic of the op-amp itself, no. It is the characteristics of the loop gain where the poles and zeros are, and what is the from there we derive what is the effective unity gain bandwidth, what is the phase margin. Okay, that's the criteria for stability, as I mentioned earlier. So if this plot here is the open loop op-amp characteristic that we have, what would be how can I plot this loop gain? The loop gain will be this red plot here, which shows that at DC values its gain is half. That means it has gone down 6 dB. So I draw a line parallel to it. It still has the same pole. I have not added any more poles and zeros. So the loop gain, poles and zeros are same as whatever the op-amp itself has. Why? Because as I said, my feedback factor is half, and I am keeping it half for all the frequencies, again as an assumption. I'm neglecting all this input capacitance here and extra pole being formed and all. So what it will do is it will take this transfer function and you have to half it down in terms of gain, and at every point you have to half it down, which means that it will just simply roll down like this parallel to this line with the same P1 location, same P2 location. But now what has happened is you can see the unity gain bandwidth has become half. So if you had an op-amp with a unity gain bandwidth of 100 megahertz, because of putting it in this configuration, because the feedback factor has become half, your unity gain bandwidth of the closed loop, okay, of this whole closed loop system has actually become half. So if it was 100 megahertz, it's become 50 megahertz. That means when this system settles, right, all the small signal settling and all that happens, that settling and all is not going to happen because of a 100 megahertz bandwidth. It will happen because of a 50 megahertz unity gain bandwidth. That is the key point to note here, is that open loop was really good, but because we have feedback of half, your unity gain bandwidth is actually smaller. So you have to keep that in mind. So when you say that this system, let's say if I have a system and you are trying to derive the specifications for the system, it's an inverting amplifier and I want a unity gain bandwidth for this inverting amplifier to be 100 megahertz. Then you actually have to start with an op-amp which is 200 megahertz. If you start with 200 megahertz, you're going to end up with 100 megahertz because the feedback factor is half. So that is a key thing that you have to keep in mind. Do not design just the op-amp by itself. You have to design the system where op-amp is a sub-block in it with all the feedback elements around it, and then design the op-amp based on that. So this is one of the first, you can call it as a side effect in this particular case, that the unity gain bandwidth of the closed loop system of the loop gain is actually half of it. Okay, the other thing, interesting thing that I also want to note here that many of us tend to miss is, so I could have actually started with an op-amp design an op-amp with whatever this unity gain bandwidth is, let's say 200 megahertz as an example. I could have started designing this op-amp with actually a bad phase margin. I could start here and say, you know what, I'm going to design this op-amp with a unity gain bandwidth of 200 megahertz and say 30-degree phase margin. And when you say it to somebody, you'll say, no, you'd never do that because that's really bad. Well, see what happens. This is the op-amp, and this is 200 megahertz point. This is the unity gain bandwidth of the op-amp. The actual closed loop system has a bandwidth which is half of it. So what matters is the phase. The phase margin does not matter actually at 200 megahertz. It actually matters at 100 megahertz for this closed loop system. So what this means is you could actually start with an op-amp which has bad phase margin, but then when you put it in this inverting amplifier loop, this guy cuts the unity gain bandwidth to half, and you automatically have good phase there. You know, the phase has not rolled off so much by the time you have gone there because you only need to look at here. You actually get good phase margin here, and that is another thing that a lot of designers exploit by saying, I don't need to start by designing an op-amp with a 60-degree phase margin, because I know that if it's 60-degree phase margin here, it's probably going to end up being 80 or 90 degree or even more than that. That is just too much. I don't need it. I could actually start with an almost unstable op-amp, and I know that because it has a feedback like this, it would end up being stable with a good phase margin number. Okay, so this is where just the open loop characteristic of the op-amp is not enough. You have to draw, or you have to understand the closed loop characteristics, specifically the loop gain, and then finally here, like what is the overall loop response will look like. This is what it will look like. You know, there are no extra poles or zeros here, so it will just have a gain of 1. It will keep going till this unity gain bandwidth point of the closed loop gain, and then it will roll down. So that's why I've got 3 things here: op-amp only, loop gain with the feedback around the op-amp, which is this red one, and the green one is going to be the actual input to output characteristic. That is the actual transfer function. If you treat everything as a black box, what is the input to output transfer function? That would be more like this green one here. So this is another example where we need to look at the actual overall system, what feedback is there, and derive it. I have got another example here which is very widely used. I've used it widely, and it took me some time also to realize what was going on. So this is of a low pass filter. So the same op-amp which we had the inverting amplifier R and R, I just kept it the same with a gain of -1. But now what has happened in the output, I've also added a pole. So this is not just an inverting amplifier, it also makes a pole at the output. And if you treated this op-amp as an ideal op-amp, the transfer function would be more like -1 divided by 1 plus S times RC. So this is the inverting amplifier gain, and this is the pole it creates. This is very widely used in the RF world, where let's say if you're designing a receiver, in the receiver, when you have the mixer and you down convert, after that you would actually have a stage like this, an op-amp RC stage, to do some filtering. Okay, maybe not there, maybe further out, but in many applications the op-amp RC type filters are very, very widely used, and that's why I think this is important. This is probably an important example to go through to give you an idea of how feedback plays into the system here too. So this will be the overall transfer function, assuming an ideal op-amp, right? We have an inverting gain, and then we have a pole where the gain starts to roll off, and at high frequency, of course, the gain is 0 because this denominator is too big. Let's apply the same thing again, and we know that what is the feedback factor here now. So this is the output voltage, let's say, and we break the feedback here. I want to know what is the feedback voltage here, right? So it's again a divider, but it's not a resistive divider. Here is an impedance, here is a resistance. So if you want to find the F is equal to what is the voltage drop across R divided by 1 plus this impedance, which is R divided by 1 plus SRC and all that stuff. So just go through, you know, the math here, and eventually we're going to come to this point for F. So the feedback factor can be arranged this way, and you can see that if, let's see, did I do it right? Yeah, it's right. So first of all, let's see if the a DC value, okay, if S was equal to 0, what is the feedback factor? It's 1 by RC, 1 by 2, and 2 by RC, right? So this will become half. So if this cap was not there, the feedback factor will be half, which is what we had previously. That's what an inverting amplifier have, and it's half because both the R's are equal, right? And then if you go to high frequency, extremely high frequency, what happens to the feedback factor? The feedback factor, this will be shorted. That means all the output, I mean not output, the voltage at this point shows up here. The capacitance will short it. So what does the feedback factor become? It becomes 1, which is what happens when S and S get divided at extremely high frequencies. The feedback factor will be 1. So at low frequencies, the feedback factor is half, where it's acting as an inverting amplifier. At high frequencies, the feedback factor becomes 1. But in between, if you look at this transfer function, it actually has a 0 at this location, and it has a pole at this location. So we get a 0, and at 2 times the 0 location, twice the 0 location, we have the pole. Okay, so let's see what the closed loop frequency response will look like, which will look something like this. Red line will come there. But let's start by saying this is my open loop op-amp, right? The normal plot with the dominant pole P1 and some P2 and some unity gain bandwidth of the op-amp. Let's also put some locations here which are this 0 and the pole, like 1 over RC and 2 over RC. We know that the feedback factor has a 0 at 1 over RC, and it has a pole at 2 RC. So this is what I'm just trying to show here in terms of the F. Okay, the feedback factor path. Let's see, am I missing? No, I think it's okay. Okay. So then now, if we know this thing, what is the loop gain? Loop gain is the product of A times F. What is A? A is this transfer function, right? This two-pole transfer function with P1 and P2. A I never write, but because if I write it, it's a mathematical equation. I think a picture tells more than writing the actual expression there. So in this loop gain A times F, A is this plot here, the open loop transfer function of the op-amp, and F is the feedback factor which we derived here. It has a pole, it has a 0 and it has a pole. So if I multiply these two at low frequencies, we know that low frequency we suffer a 6 dB loss in gain because the feedback factor is off. So I will draw the same thing. It will start here. It will hit the first pole as it is because that pole is not changing. That's the dominant pole, and it will keep going down parallel to this plot till it hits this point. See, it hits a 0. This feedback factor is adding a 0, right? So when you do A times F, the 0 in F is coming here. That's why it makes it flat like this almost. And then it hits the pole again, which is this. So it will keep going down. So here in this case, given this kind of the feedback factor, given this kind of transfer function, our unity gain bandwidth actually has not reduced. So in a way it's good news because we get the full speed of the op-amp. We are not losing half of the speed of the op-amp as we did in the previous example. But the bad news is also, like, you have to make sure that you design the op-amp by itself. Irrespective of all this feedback factor, the op-amp by itself should have good phase margin. Okay, so this becomes the loop gain plot, right? So if this becomes the loop gain plot, now we want to know what is the overall transfer function going to look like. Well, the overall transfer function is going to look more like it's an inverting amplifier with a gain of 1. So it is a gain of 1 or 0 dB. Then at 1 over RC is where the pole starts to come in, right? This will start to go down. And again, I did not mention this, but most of the time, if you're trying to create a pole at this location, so 1 over RC, the unity gain bandwidth should be roughly 10 times more than this what we're trying to create. Okay, the op-amp has to be much more faster than this pole that you're trying to create. How fast? Roughly like 10 times. Sometimes you can't do 10 times. If this is 100 megahertz pole and you want to make it 1 gigahertz, that gets harder. Maybe 5 times is good enough. But when this ratio is higher, 10 times or higher, then you don't get the non-idealities from this op-amp on this pole. If this ratio is slower, then this speed itself will try to start affecting the location of this pole, and you will not get the pole exactly at the RC location, but a little bit around here and there because of the effect from this op-amp. So coming back here, the closed loop response, so you have the plot coming in, RC pole you see it starts rolling down as a single pole response, and then when you hit the unity gain bandwidth, and this is something you will not see till when you simulate, and you will start seeing that there is a peaking that happens and goes down. This peaking is sometimes what you will see in the simulator around unity gain bandwidth. You may not care about it that far because you already caused the pole which is 10 times lower. Okay, so whatever this frequency is, this is 10 times more frequency roughly. There a peaking happens. So first of all, it could happen because of the phase margin. If your phase margin is not good, then you might start seeing more and more peaking. The second point is, can you live with this peaking? Well, if you didn't care about this far out rejection from this filter. Okay, so when you make a filter, you're trying to filter something out. What are you trying to filter? Are you trying to filter things which are close by to this pole, or do you also care about things which are say 10 times away from this pole? If you do care about any jammers or interferers that you're trying to filter, this peaking is not good. So you have to go back and improve your phase margin, improve your stability to make sure this peaking is less and less. Okay, so that is another thing that you might get surprises when you put it in. But working a circuitry this way, okay, these are approximate analysis. So working it approximately this way gives you an idea into what are the various transfer functions, starting with the op-amps itself, then with the feedback factor, then putting the whole loop gain in, what does that look like, and then the overall transfer function, what would it look like. It will give you an idea of what it should look like. So when you simulate it and you see a response which looks a little different, you will be able to interpret it, that why am I getting something like this, or why is that happening. So these are some of the examples. Hopefully gives you a little more idea about the op-amp by itself is not enough. The op-amp is always put in a feedback system. You have to analyze the whole feedback system. Okay, so last I just put a little bit about the folded cascode op-amp, but again this is something where I guess I didn't have the patience to write all the equations and draw the circuitry again and again. But this is another kind of op-amp topology that is also quite commonly used in the industry. So I will go through it. I will go through it in a more brief way, more intuitive way, what this op-amp does, how we derive some of the expressions in a simple. But again, I would suggest that please look at the literature, whether it's the Dr. Allen's book, or any other book which has more detailed analysis of this folded cascode op-amp. That will give you a lot more details into this. So why is this called a folded cascode op-amp? So this is the input stage of this op-amp, and this is the output stage. Okay, so what happens in the input stage is, these are the two input terminals. It still has the same tail current source, and I'm showing an NMOS input stage. You could also have a PMOS input stage. You can flip this whole thing upside down. But we are converting it from voltage to current here. And what is happening is we are taking this current and then we fold it down the stages. Okay, I'll explain the stages more. But since we take this current and we fold it down and eventually create a voltage, these are called folded cascode. The outputs are cascoded. The input currents are folded, and that sort of gives us the name folded cascode op-amps. So you got some sort of a biasing circuitry here, some current mirrors to provide this is the tail current. The input stage gives some current, but there is no voltage created here till it goes to the output. So all the flow here is happening in terms of currents, and when we do currents, then there are many low impedance nodes you would see here as the current flows and as we'll trace it. And finally, when you go to the output, this is the cascoded stage, which is the high impedance stage and should have the high gain, and that's how you get high gain in this folded cascode op-amp. The other thing that before going into all this I will also explain is when you do compensation, you can see there are no compensation capacitors here, because as you travel through various nodes, which you will see these are low impedance nodes, the resistance part of the impedance looking there would be roughly 1 over GM at these nodes, because we are pushing currents. Those tend to have far away poles. So the dominant pole that's going to be caused here is at the output itself, because the resistance is extremely high. It's a cascoded output stage, and the capacitance hopefully CL is also pretty high. So this creates the dominant pole, and with this capacitance itself we compensate this op-amp. So we don't need a CC to compensate this. The CL itself kind of acts as a CC and creates the dominant pole at the output. All the other nodes, which are low impedance nodes, as we'll look at, they will create low impedance poles, and hopefully they're far away where we can still get a good phase margin. Okay, so that is the other key thing to note here in case of this thing. So let me first explain how this thing works. Excuse me. So these are the two inputs, the positive input and the negative input. Let's make sure first I didn't make a mistake by doing positive and negative. Okay, so if this is the positive input, right, if this is positive, this point becomes negative. So this point A becomes negative. If A is negative, this point is negative. That means this point is negative, right? Then from here to here it becomes positive, and here is positive. Okay, good. So a positive here will give me a positive, so I have the polarities right. I didn't mess up the polarity. Let's look at what happens in the current. So when we apply a differential signal, again this common source point acts as an AC ground. So this will create a current which is GMV in by 2. This current comes here and it looks up. What does it look up? This is a constant current source. This branch here is actually carries a constant DC current, and it mirrors the current into these two branches A and B. So when my small signal AC current comes here to this point A, looking up, it looks at a constant current source, which is whose impedance, small signal impedance, is like RDS, right? So we see an RDS looking up here. What do we see down? Looking down, since this is a low impedance node, we roughly see 1 over GM, because we are looking at the source of this PMOS device. The gate is AC ground because this is a biasing circuit. So is this voltage ever going to change? No, this always remains at a fixed DC value. So this is AC ground. So if the gate is at ground, you apply any voltage at source to say what is the impedance looking into it, you will see it's 1 over GM. And I hope we have gone through it enough so you can by now know that it's 1 over GM. So the current that comes here sees an RDS looking up and a 1 over GM. Where do you think the current will go? 1 over GM is a low impedance, RDS is high impedance. Most of the current will go this way. If I say GM times RDS is roughly, 100, then 99% of the current will come around and go this way. Okay. This device also has its own RDS, so that will be another path also where this current could get lost. But again, it's an RDS here, and hopefully not much gets lost here, because this 1 over GM is actually, hopefully, is a much lower impedance compared to whether this RDS here of this device or the RDS of this device. So I can get almost all of the current to come here. Okay, maybe not 99%, maybe 98%, something like that. Okay. So now when it comes down, what does it see here? See, this stage here is a current mirror stage, right? We have seen this, where this and this eventually, this is the cascoded current mirror. So the current that comes in gets mirrored from this side to this side. So now we have a current flowing down, which is GM times V in by 2. How about this current now, the negative side? So the negative side has the same current, GM V in by 2, and that's coming here. What are the various things we see again at this point? We see an RDS looking up. We see a 1 over GM looking down roughly. Okay. And we also have an RDS of this device itself where some of the current will get lost. But majority of this current, what will happen is it will come actually and go, go through this device, right? So this current is coming and it will turn around through this 1 over GM and come to the output node. What happened to that current? That current was going away from the node A. That means it was going through this guy's up, right? This device was carrying it up and going away So if this was carrying up, that means this current mirrors were also carrying it up, right? So we have one current that's coming into the output node from top to bottom, the other current coming into the output node again from bottom to the output node. They both combine here, and finally at the output we will see an extremely high impedance, which is of cascoding, right? So we can find the R out, which is what I've tried to find out, but before that I hope you can just to rewind this lecture a little and again go through the explanations again of how the currents are flowing, and they go through the low impedance nodes and come over there. Okay, let's look at how do we find the R out here. Okay, here since there is a lot of transistors, you can all mark them as M1, M2, M3, M4, and you will have a lot of GM1, GM2, GM3s, RDS1, RDS2, RDS3 and all. It will just become very complicated, so what I tried to say is, let's just make an assumption, and it is not true in the design. This GM and RDSs are not equal, but just for the sake of showing you that how we can come up with some simplistic answers so that you understand. I'm assuming that all these transistors are the same GM and RDS. Normally the output stage will be biased with a different current than the input stage in many cases, so you're not going to have the same GM of the input stage and the output stage, but here for simplicity I'm just assuming GM and RDS to be same for all the devices. So let's look at what is the output impedance here. We know that these two currents are eventually making it up here and adding, but I need to know what is the R out to find the DC gain. So if I have this, if I look down, right, this is the output looking down, that will be roughly GM RDS square. If I look up, what I have is I have the PMOS, then this is the RDS of this current source, but this point is also shunted by another RDS. Okay, so there are two RDSs. So if you have two RDSs, it becomes RDS square, right, by 2. I'm sorry, not RDS square by 2. So if you have two RDSs in parallel, it becomes RDS by 2. So what will be the output impedance looking up? It will be roughly GM RDS square by 2. So we have the impedance looking down, we have the impedance looking up, so output impedance would be roughly GM RDS square by 3. Again, the output impedance I'm showing you is a much simpler expression because all the GM RDSs are same, but if they are not same, it will be a much more complicated expression, but you can find it out from this picture. They might all have different RDS names. Just plug it in and find the total output impedance. Okay, so if you know the output impedance, then we know that all we have to do is multiply that by the GM of the input, and it would roughly give you the gain, the DC gain, which in this case, since my GMs are same, it will be GM RDS square by 3. So you can see that even though it looks like a single gain stage, the currents as it were flowing at node A, this is a low impedance node, there is no voltage swing there, there is no voltage gain. At node B, there is no voltage gain, there is all currents flowing, these are low impedance nodes. These two nodes here, they are low impedance nodes. So all these nodes are low impedance nodes. We were pushing current, but the way these currents are combined at this output, and it's cascoded, has got an extremely high output impedance, we have got a gain which is GM RDS square. Means it's almost like saying you have two stages cascaded, each having a gain of GM RDS, GM RDS. So from a single stage itself, we are getting gain equivalent to a two stage. So this is no less gain compared to the previous configuration that we saw, which had two cascaded stages with Miller compensation. So that way you can find the gain. And about the pole, as I mentioned earlier, the dominant pole here is going to be because of this dominant output resistance here, and CL. Because all the other nodes, the impedances at all the other nodes is roughly 1 over GM. And if it becomes 1 over GM, then you just you have to assume that those poles are far out. Okay, so the dominant pole in this case becomes roughly 1 over RC, which is R out, the big expression, and the total CL. And then if you find the unity gain bandwidth, the unity gain bandwidth is given by roughly the total DC gain with the dominant pole. DC gain is GM times R out, right? This is the GM in at the input, and pole is this one here, where R out will cancel, and you will have GM of the input by CL. And this is where I have a note called self-compensating, because this op-amp with enough amount of CL, enough amount of load capacitance, is going to compensate itself. You do not need another CC type compensation capacitor to compensate it. That's why these folded cascode op-amps are also called self-compensating op-amps. Its own load helps to compensate itself and helps create the dominant pole. So this is create the dominant pole. But where are the other poles? You can work it out. You can work it out by saying each of these points is going to be low impedance 1 over GM. I need to know all the parasitic capacitance, all the CGSS, all the drain to bulk and this and that. And at each point, and this will actually have a lot of poles. You know, this point A has a pole, point B has a pole, which will be roughly all the parasitic capacitances. So for pole A, it will be roughly minus GM by all the parasitic capacitance of the node A. Similarly B. What I have not shown here is there are other poles. So this point will have a pole too. This point is also going to have a pole, right? So we have 1, 2, 3, 4 poles that I can see. Then this will have another pole, which is the 5th pole. So there is going to be a lot of poles that come up here. All these poles are far away. That is what we are assuming, right? They are far away from the unity gain bandwidth. The dominant pole is this, which defines it, and GM over CL gives you unity gain bandwidth, and all these other 5 or 6 poles that we calculate are further out, which do not affect much on the phase margin. And as long as that assumption is true, this will be great. But if your unity gain bandwidth is pretty high, and all these poles start causing, it's not 1 or 2 poles coming close to you, it could be 4 or 5 poles coming close to you, then your phased margin will degrade really, really fast. That's when then, you know, this kind of a design will become a challenge. If you can't keep these 4 and 5 poles that we have, the parasitic poles that we see here, the extra poles, away from the unity gain bandwidth point. So this is briefly a little bit of into the folded cascode op-amp, and how, you know, it's still, even being a single stage, it gives you gain, which is similar to a 2-stage op-amp. It is also self-compensating. It also has similar properties for noise and common mode and all that, which I would encourage you to look into more. I have not really put anything. I just put a single page here to do it, which I think is not doing justice to this topology. But I guess this is something that I would like to talk more and more, not in a video lecture, but maybe in a classroom with you all, and get into more details of this. But in the meantime, feel free to look at the literature in the textbooks and all, and see all the detailed information that you would find there. And hopefully my lecture has been helpful to give you some initial idea, some initial information on this folded cascode type of an op-amp topology.